As always, a little meditation is in order whilst I set up my stream. I'm going to get into some good stuff. We shall delve into the depths of calibration, interferometers, interesting light physics stuff that, believe it or not, I wasn't aware of and have never seen in any other video, except luckily I was doing a little bit of research this morning and discovered something else again about these interferometers, which I wasn't aware of, and it has to do with calibrating them. So I don't know why, like this experiments that I'm looking at on this particular website, they're using two mirrors and they're adjusting the mirrors into a beam splitter. Now, you know, this is weird because my setup actually has a beam going down through a slit into two mirrors before it hits the beam splitter. What the hell is going on here? This just popped into my head right now. I'm like asking myself, why are they using two mirrors? So I have no idea in these videos why they're using two mirrors. Now, I know why I'm using two mirrors prior to going into the beam splitter is because I want to use the second mirror. I want to use, that's probably too loud, the grating into the beam splitter so that I can adjust the color that I want to use. So, and when I looked at a little bit of the beginning of the video, they also mentioned that the wavelength that was used was not being taken into consideration. They're just using one wavelength, and that's the laser, to tune it. So what that implies is that when you change the wavelength, you're also changing the tuning. And evidently, now I was aware of being able to tune the grating across the beam splitter. And I was also aware of the way the angle of the beam splitter changes. But what I was not aware of is this dot that seemingly, depending on how the mirrors are oriented, the dot will vibrate back and forth as the second oh, now wait just a minute so they have that beam going onto, they don't have it going into a beam splitter, they got it going into on a piece of paper. So we're gonna watch this video, and there's some other videos on this channel. These were like 9-10 years ago, and I don't know exactly what they're doing, but I do feel that it's important and relevant to calibrating of my own interferometer. And I just realized now that the second mirror that he's got going up here is not pointed to. Yeah, anyway, let's just go ahead and grab this video here. I don't know why it's actually not showing up here. I'll go ahead and get rid of this and get this party started.
Polarization change between the incoming and the outgoing beam. To obtain a high fringe visibility, we need to make both density and polarization between the two beams similar. Before we start, let's go over the components we are going to be using during this video.
Alright, I'm gonna skip that. He's using some fiber optic stuff and whatever.
We have pre-collimated using a monochromatic laser. One, to feed the light into our system with to couple the laser back into a fiber. 4 flat mirrors mounted on kinematic mounts, which 2 we're gonna use to align the laser with to make it the incoming laser beam parallel to the sliding guide.
Okay, so I have the up on the upper left. I don't know if you can see that with my arrow. On the upper left, there's the laser coming in. It hits the first mirror, bounces off of that into the second mirror, but the second mirror I don't think it's going into the beam splitter because he says that it aligns, the mirrors have to align to the path of the that secondary mirror, which in my case is going to be the calibration mirror, which is down at the bottom. But I don't see, he's got this paper on the upper part up here, and I don't know if the beam splitter's not lined up with the paper here.
And the other 2 flat mirrors to couple the fine adjustment of the alignment using the oscilloscope. Maximize the mounted one of the retroreflectors on the card. We have also fixed the beam splitter such that once the beam splits in two, the reflected beam goes towards the direction in which we're gonna place our second retroreflector. We have also fixed our pre-collimated coupler, and we have connected it to a single mode fiber optic which passes through polarization pedals. We can now go ahead and connect our alignment laser to feed it to the system.
Now some of the stuff I don't have polarization into the, he's got a polarizer at the very beginning of the setup. Something I didn't really think of. I really don't want to do that because I want as much possible information coming through the slit as possible. And here I mean, you could limit the information by putting a polarizer up there or whatever, a filter, whatever, to have a cleaner signal going through and eliminate the grating and put a mirror in there. And then once the calibration is done, all you got to do is take the mirror out and put the grating in, type of thing. Oh yeah, I don't really have the ability to do that. I mean, I do, like I could, but if you move things around, it's going to go out of calibration. So there has to be a means of tuning these mirrors outside of the case. That's going to be an engineering challenge for me. I sort of have the ideas, but I don't know exactly how that's going to work yet. One idea was to put a motor setup in there, but I want the least amount of stuff inside of this enclosure as possible. My idea was to use these fine-tuning screws, and he's got a setup for these mirrors where you can adjust them in one of the other videos, but that requires me going inside of the enclosure, and the enclosure is going to be temperature controlled, temperature, humidity controlled. It's all going to be a very stable environment. So how exactly I'm going to do that, I don't know, but we're learning the basics here.
And now we can introduce both alignment mirrors, and by guiding yourself using the holes on the optical table, we want to make 2 90-degree angles such that the beam can go passes through the beam splitter, hits on there in the retroreflector, and then we can place a viewing screen to keep track of our angles.
Oh, okay, so this is exactly how my setup is set up. So it goes to the first mirror on top, then it bounces off to the second mirror. But I didn't realize that he's actually using this to tune the laser parallel to that mirror. I mean, I made an assumption. Now he's got the crosshair on the opposite side of the beam splitter. My crosshair is going to be down here at the bottom. The orientation of the beam splitter will be different. The orientation of mirrors, that's going to be different. It's just going to be, it'll be the same setup, but it's just oriented different. But he's got something interesting here. On this end, there's no mirror. He's got this little chart thing to see the laser, and then he can move this mirror back and forth like really crazy. And I'm talking, I can't breathe. So I want 12 inches from that beam splitter. This is almost like my setup, except the two mirrors are going to be much closer together, and I don't think that makes any difference. It might make a difference in the sensitivity of the setup, and I do have the availability to increase those distances. And it looks like, to be honest with you, that looks like it takes up about half the distance of my enclosure in the first setup. It's possible because the beam splitter is going to be at the end of the enclosure, 2 inches from the end, and then I'll have my 12 inches to the bottom and back to the front. So this, I think you said this was the detector side. I don't know, but anyway, let's just go ahead and watch this.
So again, using the holes to make sure we have a 90-degree angle. We're gonna place our first mirror, and we have to also make sure that the beam hits close to the center of the mirror. And the same thing we did for the first, we have to do it for the second mirror. Once you have your signal, you can go ahead and fix both the mirrors. Once the second mirror is fixed, we can observe the behavior of our signal as we move the retroreflector back and forth. Our goal is to find the...
So he calls that second mirror the retroreflector. This, in my case, is going to be the mirror on the bottom, 12 inches. The mirror on the front is down towards the bottom of the web page, but I don't know that for sure exactly. I think he's putting the detector up here where this paper is. So that's essentially, like, I don't really know what he's doing, where the other mirror is. There's another mirror that's supposed to be there. There's supposed to be two front surface mirrors, and he's only using the bottom one here.
Position that minimizes the displacement of the beam as we move the card along the rail.
Yeah, wait, let me go back. Watch that dot up there.
To the center of the mirror, both the mirrors. Once the second mirror is fixed, we can observe the behavior of our signal as we move the retroreflector back and forth. Our goal is...
So he calls it a retroreflector. I call it the calibration mirror. So that dot up there is going diagonally from the bottom to the top, left to right, which I had no idea it was doing this because of the relationship or whatever. But so the idea is to tune these two mirrors to get that change in the dot to become a zero change. In another video that we're going to see, that dot is actually a circle, and he's tuning it better with another camera setup.
Is to find the position that minimizes the displacement of the beam as we move the card along the rail. As you can see on the viewing screen, we're having a diagonal motion. This means we have to adjust both the vertical and the horizontal knob of the kinetic mount of our second mirror. Let's start with the vertical displacement. First, I'm gonna adjust the vertical knob until we have only motion on our horizontal mode. As you can see,
that's a little bit confusing, but So vertical is exactly like he says. It's up and down on the mirror, and horizontal is across. So I think I have. I mean, I understand. What I should do is actually let me just go ahead and write this in on my notepad and continue my lovely note work. And my pen, of course, I can't reach it. I'm gonna grab me a pen here. I should grab a drink too while I'm at it. Use my pen. Let's go ahead and throw a light on the subject. Oh, that was a little bit ironic. What the hell? That was fucking stupid. Meaning, I had to turn my desk lamp on. I'm like, put a little light on the subject. Wait, that's just really too ironic because light is the subject. Oh boy. So, so we'll say interferometer alignment, and then we'll put down. So we got the beam, blah, 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 and it goes in here, and this is this is M1. No, this is not M1. I'll call it. I'm gonna call it EM1 for entry, and then this one here. And then this is the beam splitter. It's not the correct orientation. And then this is M2. And then over here, we're gonna have the white card with the graph. So we've got vertical and horizontal of both mirrors to minimize dot displacement. And the stuff goes down here. This goes in here. And then this is the mirror here. It's mirror 2. But I want 12 inches from BS to M2. I'll just make that a little bit of a side note. And then so this would be H. And that would be V. H. And V.
See, if we place the retroreflector on our initial position, if we move along, our signal is moving up. That means we want to adjust this knob and move the signal down. And we keep doing this until we only see in horizontal motion. That looks fine. Now we do the same thing with our horizontal knob. And we keep adjusting. Again, it's moving to the right. So I'm gonna move it to the left. And I'm gonna keep adjusting this until we have no motion.
Oh, so there's no motion.
There you go. Once your signal is
cool.
stationary,
Okay,
we are done with the course alignment.
He can put
For
that secondary mirror anywhere he wants on that ruler, and Okay, yeah, it doesn't matter. He's adjusting that.
In
That's
alignment, we would need to observe our signal through the oscilloscope. For that, we first need to couple the light back into a fiber. The coupling of a laser beam into a fiber has already been thoroughly discussed in a previous video. Therefore, here I will just give you a brief introduction. First, we have already switched our alignment laser to feed the monochromatic laser into our setup. So now we're going to connect our alignment laser into the back end of our multimode fiber, which is connected to our fixed receiving coupler. And we're going to introduce our two coupling mirrors by making two 90-degree angles of our red laser back into our beam splitter. And then we're going to fix our coupling mirrors. Once you have fixed...
okay, that I don't understand. Why is he... that I don't know why he's doing that. Because that's not part of my system.
both coupling mirrors, we now have to adjust the knobs on our coupling mirrors so we can couple the light back into a fiber. To do this, we're gonna use our infrared card to keep track of our monochromatic laser, and what we want to do is overlap the two beams at two different ends. One before our receiving coupler and one after our beam splitter. We're gonna do this by adjusting the mirror that is always the furthest away from the viewing card. Let's start adjusting this mirror. So we place our viewing card in front of our coupler and overlap the two beams together. And now I'm gonna do the same thing, adjusting this mirror and overlapping the beams in this at this end before after the beam splitter. And you're gonna keep doing this process until you have both beams overlapping each other at the both different ends simultaneously. Once the both beams overlap at the two different ends, we can go ahead and disconnect our back end of the fiber and verify that we're receiving a signal. If you're not seeing the signal in the couple, that means that you have to go back and keep adjusting it until you get a signal. Once you have coupled the signal back into the fiber, we can go ahead and connect the other end of the fiber into our photo detector and the photo detector into our oscilloscope. Once you have connected it, you have to make a small adjustment to using the knobs on our coupling mirrors so to fully maximize our signal. Once you have adjusted and fully maximized that coupling, you have to also make sure the beam is going at the correct angle back into our fiber. To achieve this, we use a process called walking the beam. Walking the beam is done by offsetting the signal of using one of the mirrors and then compensate it with the other mirror. Since this process was already explained in the video I mentioned before, we have already maximized our signal by whacking the beam, and we can now move on to the fine adjustment. Once you have coupled the signal back into the fiber, it's time to move on to our final alignment. For that, this is gonna be just as we did for the coarse alignment, just now we're gonna use the oscilloscope. And just as we did with the coarse alignment, what we want to do is observe the behavior of our signal as we move our car along the rail.
Well,
as you can see, we're losing a lot of light, a lot of signal as we move the car along the rail. So that means we still have to do some adjustment on our alignment mirrors to make our beam parallel to our rail. To do this, we're gonna work in two different spots. We're gonna be adjusting both alignment mirrors. And the way we're gonna do this is when our car is the furthest away from the beam splitter, we're gonna adjust the mirror that is the furthest away from our coupler. And when our car is closest to the beam splitter, we're gonna adjust the mirror that is closest to the coupler. Let's try right now and just move it the furthest away. and adjust the mirror that is furthest from the coupler. Okay. Once you have maximized it, you move it again closer. And now, as you can see, the signal changed, so we're gonna adjust our mirror that is closest to the coupler, get our signal back, and we're just gonna keep doing the same thing until we have a minimal loss on our
I don't know what he's doing here.
as we move the car along the rail.
Oh, he's adjusting those two mirrors up there. Making another adjustment, a more finer adjustment.
Now, as you can see, as we move our car along the rail, our signal we lost really small little signal. So that means now we are done with.
So what he's got here, what the hell is this damn cable? Jesus. I hate these stupid ear cables. So in place of the card, he's got the photo detector on it's not lined up with the beam splitter though. Oh. Yeah, I don't know what that detector thing is doing, honestly. I have not a freaking clue. I don't know what's going on with those other two fucking mirrors.
With the fine alignment, and we can go ahead and add our second retroreflector to create some interference. As you can see, we have already attached our motorized stage up to the optical table, and we have already mounted our second retroreflector on top of our stage. Our goal in this part is to overlap the two beams so we can recombine them and create some interference. In this case, I'm gonna use the viewing card to track the signals and then adjust the vertical and horizontal knob of our second retroreflector until we overlap both signals.
Okay, so
once you overlap the signals,
he's got that Fabry Perot inside this case, and there's two. I don't know what the fuck that is because he's not explaining it. Unless if it's going into the beam splitter from the top down, I don't know.
See some interference. Once you have some interference, you can remove the viewing card, and we can now use the oscilloscope to further increase our signal. Let me just zoom this out a little bit. And now we keep adjusting our knobs until we fully maximize our signal. You can always guide yourself using the peak-to-peak value on the oscilloscope to know which direction you're going. We want to further maximize the peak-to-peak value. Once you have fully maximized the interference by overlapping the two beams, we can go ahead and move on to adjusting the polarization. To adjust the polarization, we are going to be using our polarized beam splitter, or you can also use a polarizer. Now we have to adjust our polarization in two sections of our setup. First, we have to adjust the polarization on our incoming beam. This is because even though we're using a non-polarizing beam splitter, the coefficients for transmission and reflection might be different depending on S or P polarization. To make our incoming beam either S or P polarized, we're going to place our polarized beam splitter or polarizer right in front of our coupler. And now we're gonna adjust the polarization pedals until we have fully minimized our signal.
Minimize the signal?
Now, as you can see, all of our signal should be being reflected towards this direction, and we should be getting almost no signal from going to our setup. once we have made our incoming beam either S or P polarized, we also have to adjust the polarization that is being introduced by our retroreflectors. What I'm gonna do is I'm gonna move this beam splitter, the polarized beam splitter, and I'm gonna put it in front of our receiving coupler. Now, to adjust the polarization, what I'm gonna do, since even though we have our couplers already pre-collimated, the collimation might not be necessarily perfect. So what we're gonna do is I'm gonna place our beam splitter up onto the farthest position. So that means that if we have fully maximized our signal here, we will have it also maximized on the other side. And for this step, what we're gonna do is we're gonna adjust the polarization being introduced by each of the polarizers. For that, we're gonna take, you can take a blank piece of paper to block our signal from one of our retroreflectors. And once you have blocked the signal, what we're gonna do is we're gonna adjust this retroreflector, and we're gonna rotate it until we have fully maximized our signal.
That's a mirror on the bottom.
I'm gonna go ahead and rotate it.
That's the second mirror, the first mirror. That would be what I call the test object mirror, which is towards the front of the case. Holy shit.
Okay, that seems good. Now we're gonna do the same thing with our other retroreflector. We block the signal from this one, and we will rotate this retroreflector until we have fully maximized our signal. Now, we have to verify that the signal is close, approximately the same for both retroreflectors. As you can see, they're both close to 1 volt, but we should be careful also by placing our polarizer or polarized beam splitter, as depending on the angle, this can affect our signal. So I'm gonna go ahead and remove this. As you can see, right now we have a really high fringe visibility. In order to calculate our fringe visibility, what we need to do is take our maximum and our minimum, and we're gonna take the difference between the maximum and the minimum and divide it by the addition of the maxima and the minimum. Right now we have a maxima of approximately 7 volts. So as long as we have a minima less than 0.37 volts, we should be really high on our fringe visibility, at least at 90%. You can always try, since we rotated these retroreflectors slightly, this might move the position of our retroreflector, so you can always try to adjust here and see if you can improve this signal.
Now see,
okay,
those are adjustments of the, he's doing adjustments of both of those mirrors, and one of the mirrors closer to the beam splitter, but he's using the screws directly on the mirror itself. Now my plan is to have a gear ratio set up where multiple turns of the primary gear causes an extremely small turn of the gear on the mirror. So you can also see on the right, as he moves that, there's a lot of noise on the signal. And then once he stops moving it, of course the noise goes away. But if you're there trying to tune this mirror, and my setup may not be quite as good, I mean, even if it's like, even if I can do this, because I wasn't even planning on getting this quite this intricate. I was just planning on using, visual, not using an oscilloscope with a photodetector. I'm not sure where this particular video is located, because this is on this guy's site, and he took this video and put it on his site. So I don't know where this video is coming from. I have to look at the beginning. I don't understand the second tuning part that he did with those second set of mirrors. He's got another set of mirrors like the first set of mirrors, and he's using because the second set of mirrors is actually going to add, well, it didn't add, it only used that first beam. Oh, those are lenses too. I don't know what the hell they are. I don't know what he was doing there. He was doing tuning of something.
Improve it a little bit. Okay. Let's adjust this knob too.
I've noticed he's got two peaks on the middle, like they're two peaks really close together. He's maximizing the size of the signal.
Since that might be it. So right now we have a really large fringe visibility. We have close to 90%.
Which is nice, but I think, so the fringes need to be lined up. They're not quite lined up correctly. You should see 3 peaks, and what he's got is 6 peaks. So those 2 peaks need to come together somehow, and he doesn't really explain that.
And as you can see, the visibility is being maintained actually it gets a better fringe visibility.
Hello. I noticed, did you see what happened when he moved that mirror?
That might be it. So right now we have,
let me I'm gonna slow the speed down to half speed here. Watch what happens when he moves that mirror.
Really large fringe visibility. We have close to 90%, and it's
okay. So again, you've got 6 peaks, and there should only be 3 peaks, or something else is going on that I'm not quite aware of. And what I'm looking for is the central peak to actually be minimum, which it is. And I don't really know if that's pertinent to what I'm doing, or is it better, I think, just to go ahead and get the peaks lined up, you know, so that there's only 3 of them. But that would put the center peak in the middle. And I was actually wondering about getting rid of that, but anyway.
So you can see the visibility.
Okay, see now he's moved this second mirror like a lot. I mean, a crap load of space he's moved this. And so now what's happened, he's got some peaks that are almost the same size on the right here. And the center peak is pointy. And, you know, there might be a space in there where the center peak can be eliminated. It can be minimized. And I don't know if that's something, you know, he's moved that mirror a lot more than, like, I don't know, that mirror adjustment. He's only moving it to show that the intensity is the same across the board, is what he's doing. Maybe that's just the first part of the test, and the rest of it he didn't really talk about.
He's being maintained
Okay, see now the periodicity's changed. Now see that right there? You can see like 2 little tips here. It's very close. And that's telling me that at this point, very close to this point here, the waveform is symmetrical all the way through. Oh no, wait a minute now. Wait a minute. I don't know that. I don't know that. It looks like the center beam is actually larger in width than the two side lobes. The side lobes are narrower. I want this setup on my system. I want this setup, but look where the mirror is. It's almost like halfway. Like it's a major distance. And I wasn't planning on moving that mirror that far. That's crazy.
Actually, it gets a better fringe visibility.
Now it looks like the center beam is narrow and the side lobes are a little bit larger. Yeah. Interesting. I've learned something new again today. I hate learning shit because I gotta reincorporate it into my setup.
And
yeah, that center one looks narrower. I don't know. You'd have to micro adjust that and find out what the hell is going on there with those. These are the fringes. Monitored through the second mirror that's on the top here, where he had the card, and he's got that tied in by fiber optic cable into the oscilloscope using the photo detector. I want to see that shit.
throughout our entire race.
Now see here, it looks like, okay, you know, I don't really know about these two other lobes over here on the end. You have to look at this in terms of a Fourier transform, not a sine wave, because that's what the interference pattern stuff is doing. But in this situation here, it almost looks like the widths are the same, but I don't think they are. Aside from the fact that there's two lobes on the outside ones. I'm talking about the center and the two that's next to it. It like there's 5 dots here, and there's 5 dots here. I think it's the same because it's going to be a little bit off because the height is a little bit off on his scope. I like those dots on this graph. I think it's the same, and that center one is gone. But look where the mirror is. It's way the hell up here. That's crazy. I don't know how long that is either.
Rail of the guy. Now, again, as you can see, we
It looks like about a foot.
still have a little bit of loss of visibility. This could mean that our collimation was not actually perfect. But even without a perfect collimation, we still have more than 90% fringe visibility. So that's it for this video, and thanks you for watching. Hello everyone, my name is Jamil, and in this video I will be showing you how to construct a wide scanning range.
Let me see if I can find his. The sun's gonna take me out. I don't want to go too far down the damn rabbit hole with this. SHIT. So many people doing this shit, you know. They get all these really expensive setups. No, that's not. This is a gamer. IEVES. Applications for better interferometers. You gotta do this stuff in an enclosed environment. I don't think maybe he must have a website, but I don't see it, and I'm not gonna waste any more time looking for it. USF Solid State Quantum Optics Lab. Let me... Yeah, look at that lab, huh? Let's just check that out real quick. That's just Baylor University. There's Thor Labs. They're talking. There's a lot of information about the Thor Labs. I don't know. They're trying to sell their stuff and everything. Oh God in heaven. Okay,
One is my great pleasure to introduce today.
This. So if you look at the microscope at the transistor, you will see this extremely complicated CMOS fabricated chip with a lot of transistors over there, and even in the electronic microscope you can see how complicated this structure is. Then when I enrolled to university, the characteristic size of the transistor was already like by 10 times smaller, just 90 nanometers. It was Pentium 4. Then in the year when I defended my PhD, the characteristic size was...
Oh my God, they're talking about the CPUs. The size of the CPUs is almost as narrow as a beam of light. What the hell? Light's like 500 nanometers frequency, you know, and you're talking about the difference between two light wavelengths. Oh my God.
Just 28 nanometers. The year when I moved to United States, it was Intel Core i7. The size was 16 nanometers. And then the year when I got my first faculty position, 2018,
AMD Ryzen is
it
7
was already
nanometer?
7 nanometers.
Oh my
and,
God.
just recently this processor Apple M1
optics lab, and quantum optics is the field that studies the interaction between the light and matter. And to be more specific, the matter is...
So I can tell you right now, that's a cryogenic lab. Real super duper freaking cryogenic.
Is
I'll be lucky if I get -10 or -20 into my system.
atoms and molecules and also other solid materials doesn't hold anymore, and we will need quantum mechanics. So that's the reason that we say this the quantum optics. And for my own research field, and our research field is in the surface imaging and sensing. So we utilize both quantum physics and optics to do the surface imaging and sensing. So from the imaging point of view, we image how the molecules interact with the material. So we image how the molecules come to the surface. So the question is, why are we interested in the interaction of the molecules and material, and why do we want to do the imaging? And you can imagine one of the applications that we are interested is the catalysis. So you can think about if we have molecules come to the surface, and this is the catalyst and can convert the molecule to the other type of molecules that we are more interested. So for example, you can split water into hydrogen and oxygen. Hydrogen can be used as alternative energy resources. That's one example. But then if you really want to design the material that be able to really do the work for you, be able to convert the molecules and run the catalytic reactions, you need to know how it works.
Yeah, right.
Hello and welcome everyone.
In the setup, so we put a lot of effort into making sure that students as well. And the important thing is we always need to measure those pairs. Now, we use a BBO type 1, which means that we have time energy entanglement, which is just a fancy way of saying we have those pairs. I want to note that we do not generate polarization entangled pairs. So you need a different crystal for that, for example, type 2 BBO. I can say that we plan on developing an add-on kit where we demonstrate polarization entanglement, but that's still in the works. So now that I've shown you how to create those pairs, how do I measure them? For that we place 2 single photon detectors at the output. In our case we use our SPDMA detectors, which are in a really small footprint, which is good because you can really place the detector into the setup. And we only count events when the detectors T and A click at in a very small time interval. So assume that the detector T makes a click and a couple of nanoseconds later detector A makes a click. Then you would say, yeah, probably I detected such a pair. Now in contrast, when the detector T makes a click and a millisecond later the detector this one is, or so there are several more experiments in there, but sort of the grand finale of. But the great thing is that I can get that interference back. And so this is why it's called quantum eraser. If I'm placing a polarizer with 45-degree orientation at the output, then all photons by definition will have a 45-degree orientation at detector B. And I don't know sort of which way they took. Bear with me, I know that this formulation is not only slightly problematic, but the point is you have 2 superimposing states that describe your photon, and that gives you the interference back. Now how does that look like in the experiment? It's not very different. You still have your Michelson interferometer here. You're placing polarizers in each of the arms and a polarizer at the output.
Now that interferometer is about half the size of what mine looks like, 6 inches apart or something. I don't know.
And this is the measurement that comes out of it.
So he's got stage position and micrometers. Micrometers. Let me just zoom in on this. That's like 0.5 micrometers. A coincidence rate in kilohertz. I don't know why that scale would be up. No detector polarizer at 90 degrees. It's red, green, 90 degrees, whatever.
I'm showing coincidence count rate, and that's exactly the difference between a classical light source and a non-classical light source. And what you're doing when you're attenuating the laser is, well, you're just sort of scaling that curve here, but you're not going to change the statistics of the curve just by scaling it. So that is why an attenuated laser is not a single photon source. If it were, all those quantum optics experiments would have come 20 years earlier. But it's really important to show that because it's a common misperception that we're not interested in. Okay, so that's one of the tricks. The next one, mirrors, and that's it. Next step, you're putting in the alignment laser. Similarly with two mirrors. Now you may say, okay, this one here is in the way of the other. That's correct. So we mounted that on a magnetic platform here, so you can take it in and out of the setup, meaning you can switch between pump and alignment laser.
Jesus Christ, I gotta fucking go do some stupid shit here because this fucking moron bot. Goodbye. Have a nice life, whatever the fuck your bot's doing.
The next design idea is that we have two irises here and here that define the optical axis of the entire experiment. And now we're doing a beam walk both for the pump beam as well as the alignment laser to make sure that both of those lasers pass through these two irises and make sure they are on top of each other. There's an insights video from Thor Labs where the this method of
whatever the hell that's all about.
that we have those in the right orientation. There are two more steps in there, so you're going from the Deutsch alphabetization is one of the bits, and the one-to-one translation, our manual. So we put from the experience.
This is all
Factors
about
are
quantum
open
optics.
and free space.
And
Is there any concern?
I'm not into that right now. We're not doing that. Let's go back to these videos here. We're done with that one. Let's go with this one here.
Demonstrating how to insert a Faraday isolator into a laser beam in free space. The Faraday isolator consists of three parts: an incoming polarizing beam splitting cube, a Faraday rotator, and an outgoing polarizing beam splitting cube. Linearly polarized light incident on the incoming polarizing beam splitting cube such that the angle of polarization coincides with the angle of transmission of the polarizing beam splitting cube will be transmitted through the polarizing beam splitting cube. It will then have its angle of polarization rotated by the Faraday rotator such that it emerges from the Faraday rotator with an angle of polarization 45 degrees to the original angle of polarization.
Did you get all that?
It will next be transmitted through the outgoing polarizing beam splitting cube, whose angle of transmission is 45 degrees with respect to the incoming polarizing beam splitting cube. Light going the opposite direction will be sent through the outgoing polarizing beam splitting cube and will emerge with a linear polarization 45 degree angle with respect to the incoming polarizing beam splitting cube. The Faraday rotator will then rotate the angle of polarization such that it's 90 degrees with respect to the transmission angle of the polarizing beam splitting cube, and it'll be sent out the side. Hence, the Faraday rotator prevents backwards flow of light.
Oh, nice.
The procedure consists of 4 steps. The first step is to insert and align the Faraday rotator. The next step is to insert and adjust the incoming polarizing beam splitting cube. The third step is to insert and adjust the outgoing polarizing beam splitting cube. And the fourth step is to adjust the Faraday rotator using an adjustment knob to adjust it for the angle, to adjust it for the wavelength of light being used. The Faraday rotator uses a fixed magnet, so when sitting down on the optical table, it'll be drawn to the optical table, so be careful. Prior to this demonstration, I set up a laser beam in free space with 2 mirrors, such that after the 2 mirrors, the laser beam is parallel to the optical table and runs with the holes of the optical table. This will make alignment slightly easier. I'll be using a technique to adjust the outgoing angle of the laser beam such that it coincides with the Faraday isolator. The technique is known as walking the beam. This will require 2 mirrors, where you adjust the angle of one mirror and compensate with the angle of the other mirror. This is done with both the horizontal and the vertical angles. To get a better idea and understanding of the walking the beam technique, you can view one of the other videos where I couple light from an open beam in free space into an optical fiber. Okay, so the first step, the other videos where I couple light from an open beam in free space into an optical fiber. Okay, so the first step is to insert the Faraday rotator. So I'm going to remove the 2 polarizing beam splitting cubes and then insert the Faraday rotator into the beam. Now, to view the beam, I'll be using a near-infrared viewing card because our beam is in the near-infrared wavelength. So we can just start off by visually inserting this. Alright. So I'll move the horizontal position and then I'll lightly clamp it to the table so I can adjust the vertical position. Alright. So I need to adjust the vertical. It looks like it needs to come down just slightly. There you go. Alright, look at it. So the beam is emerging from the Faraday isolator. So now we have 2 things that we can check. We can check using a power meter the incoming power versus the outgoing power. We can also check using our card a visual representation of the beam. So we can look at the beam shape going in and the beam shape going out. Alright, so I zoomed in so the camera can see both the incoming and outgoing beam so we can compare the shapes. So if we look at the incoming beam, we can see it's quite round. Compare that to the outgoing beam, we can see that it's not quite round and it's scattering light a little bit over here. So what I'm going to do is I'm going to change the angle of the Faraday isolator or Faraday rotator to see if we can have a better alignment. Alright, so it seems to be improving. Alright, so I changed the angle slightly and we see that there's a nice round beam coming out. Compare along with the round beam going in. So now we can use the power meter to do a second check. Alright, now we can check the incoming power. Let's see, and we're here about 9 milliwatts. We can take a look at the outgoing power. Alright, and it's about 7.51, so I'm just going to use this mirror and adjust the angle to maximize this. Alright, so it looks like we're around 9 milliwatts, saying just the vertical angle now. Alright, so I think it's good enough to move on to the next step. And since we adjusted the angle, I'm going to take one last look at the beam, make sure it's still nice and round. Alright, so the next step is to insert the polarizing beam splitter, the input polarizing beam splitter. So I can put it in here, and now I just need to rotate it to maximize the outgoing power. So I'm going to rotate it, and it seems like it maximizes around 8.2 milliwatts maybe. Yeah, 0.2 or so, so I'm going to secure it. Alright, so again, it slightly changes the trajectory, so we can use this mirror to align it again. Alright. But at this point, this is not too critical, alright? So now the next step is to put in the second polarizing beam splitting cube. So I'll insert it, and then I'll put the power meter in front of it. And now we can turn this to maximize the output. Alright, so it looks like about 8 milliwatts. There we go. Secure it down. And I can adjust this if I like, but let's see, I'll adjust it slightly. Alright. But I'm not going to put too much effort into this because the next part is to do the fine adjustment, and for the fine adjustment we have to turn the whole Faraday isolator around and measure the extinction. So I'm going to turn it around. Alright, and then quickly realign it. So here we go. Take a look at the power coming out. So we can barely see the power going out, so that's good. We'll put the power meter in front of that. I have to adjust the scale on the power meter. So I'll adjust the scale. There we go. So now I'm going to turn this adjustment to find a minimum. So it looks like it's maximizing it, so I'm going to go the other direction. Let's minimize it. There we go. There you go. Looks good. Alright, so I found a minimum. So now I'm going to turn it back around and then finally align everything. Alright, so I'm going to put it back in the path. And I might have raised it a little bit while I turned it around. 0.5 milliwatts later. Furthermore, decibels, which is consistent with the specs of this particular isolator. Have to. Right, I hope.
So, in a sense, I wonder. Let me go back to the beginning. I want to listen to the beginning again.
On the incoming to a laser beam in free space. The Faraday isolator consists of 3 parts: an incoming polarizing beam splitting cube, a Faraday rotator, and an outgoing polarizing beam splitting cube. Linearly polarized light incident on the incoming polarizing beam splitting cube such that the angle of polarization coincides with the angle of transmission of the polarizing beam splitting cube will be transmitted through the polarizing beam splitting cube. It will then have its angle of polarization rotated by the Faraday rotator such that it emerges from the Faraday rotator with an angle of polarization.
Alright, so let's go ahead on this here. And look up Faraday rotator. What the fuck is this? Optical circulator. Faraday rotation. Should be crystal. Optics Faraday effect. Faraday isolator. I'm wondering, so we're building this Fabry Perot device, which supposedly provides better tuning of the test frequency. But that particular device didn't have polarizers on either end. Now, I don't know if the polarizers, and they're not going to totally eliminate the magnetic field, but I don't know exactly. I would assume I could no. I mean, I wonder if it's possible to incorporate the Faraday isolator into the Fabry Perot device and make them one of the same. Control light with magnets and olive oil. The Faraday effect. Ooh. Interesting. Very interesting. What's this Faraday effect? The Faraday effect. Polarization in France. Let me go back to up here. Optical rotator. Let me just do that one. And then videos. Wait, they got.
In this video, I'll be demonstrating how to
Faraday effect. Oh, I thought I saw this video. Faraday's magneto-optical effect. Oh, this is Faraday isolator Faraday rotator. There's a lot of shit on this. We're going down the rabbit hole a little.
Hello guys, welcome back in this new
I'm gonna pause that one.
1840s. When we place a transparent material in a magnetic field and polarized light travels through the material in the direction of the magnetic field, the polarization of light is rotated. The angle of rotation depends on the strength of the magnetic field and on the distance traveled by light under this condition. We can identify the rotation beta as V times the magnetic field B times the distance d, where V is a characteristic constant of the material called the Verder constant. This constant actually can be written as E over 2mc times lambda times dn over d lambda, where E is the charge of the electron, m is the mass of the electron, c is the speed of light in a vacuum, lambda is the wavelength of light, so it is wavelength dependent, and dn d lambda is the change of the refractive index with the wavelength, also known as the rotary dispersion. Faraday effect comes from the interaction of the external magnetic field on the motion of the electrons in the atoms of that material. The electrons move around the atoms and the magnetic field exerts a torque on those electrons that affects their trajectories. This induces circular birefringence. This means that right and left circularly polarized light travels at different speed in the material, and linearly polarized light can be decomposed into linear combination of right and left circularly polarized light. When the circular component of the polarized light travels through the material, it induces the electrons to generate a magnetic field that can be parallel or antiparallel to the external magnetic field. This makes the overall magnetic field to be increased in one direction and decreased in the opposite direction, what makes slow down one of the components more than the other, which at the end of the day will produce this phase difference beta. One of the interesting aspects is that the phase shift will be in the same direction no matter if the light travels forward or backward in the material. We can use this effect as a Faraday rotator by placing the material and magnetic field between two polarizing beam splitters and one mirror. Vertically polarized light hitting the first PBS will go straight, will then meet the Faraday rotator that will rotate the polarization by 45 degrees. It will then meet a mirror that reflects light back to the Faraday rotator that will rotate additional 45 degrees. Then this now horizontally polarized light will meet the PBS again, and now it will be reflected. This helps avoid feedback into the source of light, the laser for example, while you also rotate the polarization by 90 degrees.
A polarized beam splitter. Well, we're gonna have to go up here and look for something here. Making polarized. I can't afford all these damn beam splitters. Now I see the reason behind the polarized beam splitter. They've got those. wait. So what if I use a regular polarizer? Fuck, I think I only got one set of polarizers. If I use... See, if I have the beam splitter in front of the polarizer, I can do that. I don't have to build this. I thought maybe you could... Polarization with plastic plate. What is this? I don't know what the hell that's all about. Unless that's a refracted. A diffraction grating. Standard diffraction grating does not polarize light on its own, but it is polarization sensitive. The grating's efficiency and brightness depend on change significantly depending on the orientation and position of the incoming light. So I could use a diffraction grating. No, I can't. If the CD-ROM, because they say you can peel the back of the CD-ROM apart. Let me just go look at that real quick, because I got that broken one. Let's see, the broken one. Where is it? I gotta get me a little snack. The broken one is in a plastic case somewhere. Took one apart and it just was not in happy shape. I don't remember where the fuck I put it. Why me, Lord? What did I ever do? It's not in this pile of crap. I don't remember what I did with the damn thing. I think you can see through it. I gotta look it up on it. I don't know where it is. I gotta get me a snack and have a drink. Let's go back and see. I don't think that acts as a beam splitter though. I mean, I've got a beam splitter. I can use plastic as a beam splitter. The question is, do I need this Faraday rotator? And I want to investigate this information here. And what I'm going to do is I'm going to stop this music for a minute here and keep going through this.
It can also be used to find magnetic fields out in outer space, in interstellar medium, where you have a...
Alright, so let me talk about something that's pretty related to that, but it has some other uses as well. So this particular optic is called a Faraday isolator. A Faraday optical, those lasers are extremely sensitive to back reflections. So if any light reflects, from optics that are on your laser table and gets back into the original laser, it'll destabilize it and you'll no longer have pulses. So this is definitely something we want to avoid. And typically the way this is avoided is by using a Faraday optical isolator.
And using these beam
and so,
splitters.
like, for example, the way these things are sits in between two polarizing beam splitters. And so, like, for example, the way these things are normally designed is you've got a Faraday rotator that sits in between two polarizing beam splitters. It goes through this so-called Faraday rotator, which is basically is so. And because that polarizer is set up excitation through the polarizing beam splitter, on the right, and it will actually be projected. So it doesn't go back and transmit through the polarizer.
Take a look at this. I've got a light source here, and then I've got a polarizer in front of it. And then over here I've got another polarizer, and these are oriented 90 degrees to each other. They're crossed, meaning that very little light gets through the pair. But because they're imperfect, even at 90 degrees, a small amount of light will leak through if it's very bright. Okay, to this I'm going to add a beaker of olive oil, and then I'm going to put into the beaker a coil of copper wires, a few thousand turns of copper wire, and I'm going to lower this down in here so that we can look down the bore. Okay, so now I'm going to move the camera down to benchtop level so that we're looking through the polarizer,
so you know what he's
through the
doing.
coil, and
You
then
know what
through
he's doing? He's slowing down. He's using the oil to slow down the speed of light. So let me just go ahead and let me go over here. So we go. The refractive index of water is 1.33. This means light travels through water at about 3/4 of its speed in a vacuum. However, this value varies depending on the light's wavelength, water temperature, and salinity. The value is not that much different though, 1.33. So now what about mineral? What about mineral oil? .467. This specific optical part allows mineral oil to be widely used in application, etc., etc., etc. At 20 degrees C. God damn these fucking pop-ups. Pardon my French. Shit happens. It just says 1.4. And what about olive oil? It's about the same. Baby oil is 1.48. Cooking oil 1.46. Immersion oil for microscopy is a little bit higher. Because veggie oils share a refractive index very close to 1.47, they are often used in science experiments where glass objects such as Pyrex, which has a refractive index of 1.474, are placed in the oil and become entirely invisible. Pyrex. The mineral oil is 1.48. The veggie and cooking oil is a slightly lower. It's closer to Pyrex. Refractive index of common household liquids. Shit, what did I do? So Pyrex is roughly 1.47. So almond oil, but that's probably dark. This veggie oil that I've got is very light. Castor oil, corn oil, cottonseed, eucalyptus, glycerol, kerosene. We're not using flammable material, thank you. Olive oil, seed sunflower, tongue, turpentine, water, wintergreen. So the best is veggie oil. I got veggie oil, it's like really thin. Okay.
Our next optical element.
When the heck is that?
The Faraday effect.
That video. I lost it. I lost the damn video. Here it is.
The other polarizer, and I'm going to control the power through the coil with this switch. Crazy, right? Did you expect that to happen? I actually had no idea the effect would be so large. So at first you might be thinking, oh, it's probably a problem with the experimental setup, like maybe the coil is pulling something near it and it's, causing the light to be darker. No, that's definitely not it. And then you might be thinking, well, maybe it's a liquid crystal effect, like, the heavy oil molecules are, changing the polarization of light or something. No, that's actually not it either. It works just fine with plain old distilled water. The effect is not quite as strong as in the olive oil, but it's still there, and water is definitely not a liquid crystal. This phenomenon, called the Faraday effect, actually occurs in almost all transparent materials. And what's happening here is when there's a magnetic field in the direction that the light is traveling through a substance, it rotates the polarization of the light very slightly. So if we're sending in vertically polarized light, if we have a strong enough magnetic field over a big enough distance in the material, then we can actually rotate that field slightly. So if the two polarizers are 90 degrees relative to each other, it's very dark, almost no light is getting through. But with a small amount of rotation added in between them, we get a little bit more light through it. The effect happens in air too. It's just that air is so much less dense than the olive oil or the water, you can't really see it. And so here's the setup with just air. As you can see, there's no visual effect. Also, plain glass is not very good at this either. So here's a borosilicate capillary that I have, and I didn't polish the ends, but I don't think that matters too much. As you can see, the effect is pretty slight, but not nearly as big as the water or the olive oil. On the other hand, if we add something to the glass, this is I believe, a neodymium glass laser rod. You can see the effect is strong again. And just to really show that this is a magnetic effect, here's a permanent magnet being lowered into just plain distilled water. And as you can see, when I get the magnet close, the amount of light changes. Even more interestingly, when I rotate the magnet from side to side, when the magnetic field is in the direction of the light travel, you can see that the light is affected differently when the magnet is rotated and is transverse to the light direction. Pretty cool. It even works with just a vial of water. So if I get the magnet close to the side of the vial and then pull it away and put it back, you can see the light levels changing. So what's actually going on here? Well, the hand-wavy explanation is that all matter is made up of atoms which have electrons in them, and electrons, being charged particles, are affected by magnetic fields. So that when an incoming photon interacts with those electrons in the matter, if it's in a very strong magnetic field, everything's going to be affected, and there you go. Unfortunately, the complete description is fairly difficult and beyond the scope of this video, but I will put links in the description for those interested. If you're interested in playing with this yourself, I have a few tips for you. First, when I was looking for this effect, I used a really strong neodymium magnet and a vial of olive oil, and I tried every combination of, putting this thing around and staring through it in the dark, and I couldn't get it to work. So originally I thought that the effect was just too small to see with the naked eye. And if you look around on the net, most of the documentation is using photomultipliers or photodiodes, and I thought, oh, there's just no way you're going to see this with the eye. However, the problem is with the magnet. With a single magnet like this, you'll almost never get this to work, and here's why. So this magnet is north and south on the large flat faces, and the field around the outside looks sort of something like this. So there's actually a very small region where the field lines are parallel and strong, so that the strength of this magnet is mostly high out near the poles here, and it's weak over here. And if you put this near a vial hoping to see the effect, you'll only get this Faraday effect when the light is traveling in the same direction as the magnetic field lines, which means only this little slice right here. And since the effect is so weak, we really need these lines to be extended over a large area to view it. So what I did... Okay, we're back, and my fingers are okay. What I was going to say was that this magnet is configured a little differently so that the field has to come out from one side and then it travels through a longer distance here. And because there's north-south and then north-south again, the shape of the magnetic field out here is much more parallel for a longer period or for a longer space. There's a really cool practical application of the Faraday effect. Let's say we have one polarizer like this, and then another polarizer that is 45 degrees, not 90 degrees twisted. And then we set up our coil with the special high Faraday or high verdict constant material in there, and the rotation is 45 degrees. So what'll happen is the light will go through the first polarizer, so now it's just vertical polarized, and when it goes through our Faraday rotator, it's now plus 45 degrees, and when it hits this polarizer, which is at 45 degrees, all of it goes through. So the whole system is as efficient as it can be. However, if you try to send light in this way, it hits this polarizer, which is plus 45, and when it goes through the Faraday rotator, instead of being reversed back to vertical, the magnetic field is now going the other direction. So instead it spins the light another 45 degrees, and now it's 90, and then when it hits this polarizer, none of it goes through, or very little goes through. Pretty weird, right? There's not too many substances that do this. In fact, you've probably never encountered one where if you look through it, it's clear in one direction, and you look through it and it's opaque in the other direction. And in theory, you wouldn't really need a power source. You could do this with permanent magnets even. The problem is getting 45 degrees of rotation is quite difficult. As you saw with our experiment, doing an amp and a half with a few thousand turns is just enough to get like a couple degrees of rotation. So getting all the way to 45 degrees of rotation is not easy. The material's ability to perform this phenomenon is called the verdict constant, and it has units like radians per Tesla meter. So if the magnetic field is longer, then it's bigger, and if the magnetic field is stronger, then we get more effect. Or the material itself can just simply have a higher constant. I haven't found a good list of verdict constants for various materials, but keep in mind that gases are almost certainly going to be less than liquids and solids. It's also easier to see this with an electromagnet anyway, because you can turn the magnet on and off without disturbing the setup, so it's easier to see the brightness change. And in this case, I'm using a solenoid. I just liberated the coil from this mechanical solenoid, and I believe it's about 60 ohms, as near as I can tell, maybe a few thousand turns of wire. And we're drawing, about an amp and a half almost at 60 volts for this thing. So it's quite a bit of power. You can't really leave it on. But luckily, if it's submerged in water or oil anyway, you won't have any heat buildup problems. The last thing to consider is the quality of these polarizers. It might work with low-quality polarizers that you can get from sort of cheap, kind of home science kits. I actually got these from a polarizer manufacturer, and this was the most restrictive polarizer they make. So not necessarily expensive, but just very restrictive, meaning that they don't transmit a whole lot of light. As you can see, they're dark. They're less than 50% transmissive, but they do restrict. They have a very high extinction ratio, as it's called, meaning that when they're crossed, it's very dark. Finally, you'll have to use glass to contain the substance you want to inspect. So you'll probably laugh at me for doing this, but I made this really cool little plastic olive oil container, and this actually fits down into the solenoid coil really well. And then I found out, oh yeah, I used plastic end caps on this, and guess what? The plastic randomizes the light polarization all by itself. So you can't use a plastic container because it's going to ruin the polarization and the whole thing just won't work. But wait, there's more. You might be thinking, well, if a magnetic field affects a transparent substance, what about reflections? And yeah, it's true, actually. So if you have, a reflective substance in a magnetic field and you shine polarized light on it, will it be affected based on the polarization, or will it be affected by the magnetization of the surface? Yeah, it's called the Kerr effect, and I'll do a future video on that, but I haven't been able to see the effect myself yet because it's even weaker than the Faraday effect.
Did that say 10 years ago? Holy shit. Silver nano prisms? I gotta check that one out. He's got some good shit in here. If you like sputtering, you'll like this. Oh my god, he's got a lot of shit here, which I don't want to get into. What time is it? Not quite noon. What is that? We're talking 10 years ago. Holograms on chocolate. Oh, I saw that video there. Vacuum preloaded spherical air bearings without special tools. Diode self-mixing. Print your brain. The Zeeman control light with magnetic fields. The Zeeman effect. Rubber band refrigerator? What the hell is that all about? Worn out toothbrush. Your toothbrush is worn out. I know. Faraday effect. Control light with magnet and odor. Control light with heat and magnets.
Today on Applied Science, we're going to be doing some nuclear physics. But if we're looking for a much weaker signal, it might be down in the noise. And so then what you have to do is close the box, because around 25 watts for the transmit pulse. And everything in the circuit from here to here is 50 ohms. So we send this 50 ohm, 25 watt pulse out into here, and we use this matching capacitor. This is one of those variable vacuum capacitors that you saw in the box. And we feed that into this parallel LC resonant circuit. And the L in the parallel circuit is the sample coil. So this is that coil of wire that's holding the test tube. And it's about 25 turns. And we use this relatively thick wire because we want a very high Q. When you read articles about NQR and this technique that we're doing here, everyone talks about getting the Q of your sample higher and higher. As it turns out, there are other facets of this thing that might be even more important than the Q of the probe here. But the reason that it's a thing that you might want to worry about is that the higher the Q of this resonance circuit, the easier it is to detect a very weak signal. So what we want to do is detect just the tiniest amount of magnetic variation within that coil. And this means that when you have a high power going through here, the diodes from the start of the transmit pulse to about 250 microseconds. So what we'll do is of precession and the maximum amount of by transmitting at the characteristic frequency. It has this gyromagnetic quality from the start of. While we're collecting data from the paracetamol, let's talk about where this signal actually comes from. So imagine we've got an atomic nucleus here, and it's got protons and neutrons in there, so the net charge is positive. Recall that there's also this property called spin, and the subatomic particles that make up the nucleus each have a spin, and they combine together to give a net spin to the nucleus if for certain materials. And remember that if you've got something that's charged and it's spinning, that's kind of like a little bar magnet. It's trying to pull it down, pull it straight, and the gyroscope precesses in response, right? I mean, that's what these gyroscopes. Today on Applied Science, I'd like to show you these silver nanoprisms. Each of the colorful liquids you can see there contain silver nanoparticles, and the shape of those particles are like little antennae that catch certain wavelengths of light. This is a lot like the blue morpho butterfly wing, which actually isn't made out of a blue material. I first saw this idea on the CMD ITR YouTube channel, which posts interesting materials research from universities all over and vacuuming it, and I still ended up with this very dark, not good looking product here. And then I figured out I was using 10 times too much silver. So just use the right amount. And so the amounts that ended up working for me in a 250 ml flask, 95 mLs of water, 200 microliters of the sodium, that should say silver nitrate solution, 1 ml of the sodium citrate solution, and you degas this. Now in the video, there was a lot of emphasis put on bubbling nitrogen for like an hour. And if you don't do it for an hour, it's not going to work. If you bubble it for half an hour, it's not going to work. I found that it actually is fine. My solution there.
Yeah,
and if we
degassing.
today
So I
on
don't know
Applied
if you degas mineral oil. If you need it. And what that does is you boil it, and it boils the bubbles out, and then you can. I don't know if you can. Can you degas? I wonder if you can. Let's see here. Oops. You don't really have to degas it because it's a thick viscous fluid, so they don't even talk about it. So the unknown story, corruption, yeah. The billion-dollar product making your food toxic. I don't really use mineral oil for much.
Science, I'd like to show you a technique to etch.
Oh, that's not what I was watching. I forgot where I was at now.
Today on Applied Science, I want to. Today on Applied. In my.
I lost it now. I lost it.
Hi, I'm Rachel.
I don't even
I'd
know
like
what
to
the
show
hell
you a
video I was
demonstration
watching.
About
Oh,
light magnetism
shut
in
it, will
matter.
you?
When light travels through water, it slows down.
I don't know what the hell I was watching now. I don't know where that thing is.
Today on Applied Science, I'm going to show you how to take a laser diode and without any other optical component.
Let's just go in order again.
New experiment. Today we're dealing with a Faraday rotator. We have here a helium-neon laser, which is linearly polarized. We have these two coils that will generate a pretty high magnetic field in this region. Then we have a beaker that is filled with olive oil, and this is just to amplify our effect.
Holy
Here we
shit.
have a linear polarizer and then a screen. Here you can see the beam.
Look at the amperage
And
he's
nothing.
got
I will turn
going
off the
in
lights
here.
and
Oh
see
my
what
fucking
happens
God.
when I turn on the magnetic field. What I expect is that we should achieve a variation of the intensity of the beam on the screen due to the fact that we are changing the angle of polarization of our
The other guy
helium-neon
only used 1 amp.
after our system.
Oh my freaking God.
Okay guys, I have turned off the lights. Here you can see everything in the dark. This one is our beam on the screen. Okay, I'm gonna turn on the magnetic field. Okay, you can see that when I turn on the magnetic field, the
What the fuck?
Silicon wafers to make optical filters to that's similar to a single coating like this. But the difference here is that the waveform actually controls the index of refraction as we're etching the silicon. I can't think of any other material that does this, so we'll see. It's a pretty cool thing. Also, this entire project was inspired by a viewer suggestion, so thank you so much, Ian, for suggesting this. This turned out to be a tremendous journey into how math ties together spatial and frequency and temporal, and it's really quite a thing. So pull up a chair and let's take a look at some optical coatings. I'm going to say index a lot in this video, and what I mean is the light ray just goes completely all the way through. Big camera lens like this, there could be 10 or 20 interfaces to deal with. So 0.95 to the 10 or 20 power is pretty bad. This 180-degree canceling wave. To notice are that the response is very smooth. So greenish because there is in fact less red and less blue light compared to green in this case, because now we're correcting frequencies in the red and blue area, but we're at gate filter. Doesn't have to be a sine wave, kind of whatever conditions you've got. The N-type wafers are photosensitive, which could be interesting if you wanted to pattern this, but it still adds another wrinkle. There are quite a few different kinds of silicon wafer in the world, and the ones that work best for this experiment are P-type that are heavily doped. And that's not a Cheech and Chong reference, that just means that these are...
Okay, we don't need to get into that.
I'll show you one of the coolest things I've seen in a long time. With this apparatus, it can accelerate electrons and shoot them out through a special aperture into air, and we can see the beam there. And then also we can put things in front of it, like a phosphor screen. This one came out of an oscilloscope, and actually see the effect working, just like a cathode ray tube, but it's in air. So in today's video, I'm going to show you what this special aperture is that allows this to happen, how I built the thing, and industrial uses for electron beams in air. You might be surprised, but in your house there's probably multiple items that were manufactured by being irradiated with electrons. Let's talk about how this thing is built. We're going to create the electrons in the conventional way in a vacuum area, so we need a pretty good vacuum setup. So I have a turbomolecular pump here, this cross-fitting vacuum gauge up here, some electrical pass-through back here. Hysol 1C, which is a special kind of epoxy that's made for high vacuum applications. It's actually really high-quality epoxy that you can use for all kinds of things, and I also bought it on Amazon. It's about kind of epoxy that's made very flat to interface with this special aperture. I used Hysol 1C, which is a special kind of epoxy that's made for high vacuum applications. It's actually really high quality epoxy that you can use for all kinds of things, and I also bought it on Amazon. It's about $15, I think. So let's talk about this special aperture. What is it about this thing that allows electrons to come through? Let me show you. And here it is. Believe it or not, it's an off-the-shelf part that I bought from Ted Pella, and they are specifically made to allow X-rays and electrons through. It's a window, and it's a super, super thin window. It's almost the thinnest window that you can get. And the reason I say that is because these are only 100 nanometers thick, which is like, what, 500 atoms thick. So I've seen these windows available in thinner versions. I think you can get them down to maybe 30 nanometers, but eventually you just kind of run out of atoms and you can't make it any thinner. So this is really getting down to that level. And as you can imagine, it's very fragile. You can't touch them or anything, but they are strong enough to hold vacuum. So 100 nanometers thick with a 1 by 1 millimeter aperture, which is what these are strong enough to hold vacuum forces. In other words, we can have vacuum on one side and 1 atmosphere of pressure on the other. A etched side, and I've heard that the etched side could go towards vacuum and the flat side should go towards your, if you have time on the Large Hadron Collider, thin, just so it allows all of those electrons through and doesn't end up.
Have a nice day.
And this magnet has holes going transverse through and vertically through, so that I can position this over the flame like this, so that the flame is going up through the magnet, but we can still see the light through the holes in the side there. So let me move this out of the way so we can see something else for a sec. You've probably seen the trick where you dissolve some sodium nitrate or even sodium chloride in water, and then just use a little bit of shoelace or wick to introduce sodium into the flame like this. And this works just fine. But for today's demo, I'm going to use a little ceramic rod that's been heated up very hot and then dipped in salt. And the reason that I do this is that the flame that comes out is way more stable, so there's no spattering because there's no water involved. Okay, now with the magnet in place, the sodium in the flame, if you look down the barrel and turn the magnet on and off, this is what you see. Pretty cool, right? The first thing that's weird is that the flame is actually obstructing the light that's coming out from the sodium lamp. And then you can see when I turn the light source behind it, and this opaquing effect goes away because the lines don't line up anymore. In science, I'd like to show you an unusual property of rubber bands and also demonstrate a mechanism that I built that makes use of this property. So here's what you can do. You can try this at home. Just go to your office drawer and pick out a couple of regular rubber bands. The bigger the better. This one is a size 64. And what you want to do is stretch it really hard and then hold it up to your lips. So let's switch to thermal vision so that you can see what I feel. And so here's the rubber band, and it's kind of at room temperature. The scale here is about 27C to 34C. Now if I stretch it really hard, you can see that the rubber band actually warmed up. And if I hold it to my lips like this, it's warm. I can feel it. It's quite noticeable a change.
Yeah.
So you might be thinking, well, that's not that exciting. I mean, it's probably just friction in the rubber, you know, car tires heat up and all this. However, if you keep the rubber band stretched like this and either blow on it or just hold it out in the air for a while and then let it contract, watch what happens. It actually gets colder than room temperature. And if I put it back up to my lips, it's noticeably cold. So when you try this, stretch it really hard so you get a good difference. And then, like I say, blow on it a little bit so that it comes back down to room temperature. And when you let it contract, it's definitely cold. What a weird property, right? So I'll let you think about why it does this. At first, it might seem counterintuitive because if you know, gases get cold when they expand and get hot when you compress them, it almost seems like the rubber band is doing it does in your refrigerator. So I searched around to see if the boundary of the box, this whole system can work. And I know the sealing is not going to be that great, of course, but really it's just a demonstrator just to see if this thing can work at all. One thing that's nice about having a router is that you don't have to cut all the way through the material. Like the stretch of the rubber bands is a little too much. So when I was prototyping this, I had a little jig on the table and 5 minutes or something like that. And you can just barely. Previous video, I said that a magnetized object will actually affect the light that is reflected off its surface. And I've spent a lot of time searching for a way that I can capture this on video and show it to you. And so today I was finally successful. Here's the setup. We've got a polarized light source shining down on this computer storage disk. And then the camera is looking down through another polarizer at the spot on the disk. And the two polarizers are oriented such that very little light is making it through. So the polarizers are crossed. And then I've got one of those evil, scary magnets underneath the disk so that the field is facing up through the disk. And then I've got a laser pointer with a lens that's purposefully skewed on it, so that when I shine the laser through here, I end up with sort of like a cat's eye spot, like an elongated dot. Okay, so now take a look what happens when I shine the laser on the disk. Pretty cool, right? I mean, you can see there's a temporary effect. So the laser is actually heating up the disk, which is polycarbonate, and thermally stressing it, which is what's causing that temporary effect. But check it out, there's actually a permanent effect too. So after the laser spot has moved on, you'll see that the disk actually retains sort of a track of where the laser has been. Pretty neat. Now I tried to control very carefully for this. At first I thought it's probably a thermal effect. It's probably not the real magneto-optical Kerr effect. So I removed the magnet and repeated exactly the same thing. This is the same setup, the same laser, same lens at the same angle, everything. And as you can see, without the magnet in place, when I bring the laser over the disk, there's no permanent effect. So you can still see the temporary effect, so it's still heating the disk up because the laser is focused to a tight spot, but it's not creating tracks like it was with the magnet in place. And I've gone back and forth many times, and I've convinced myself that this is the real magneto-optical effect. But I wouldn't be too surprised if there was something else going on here, because the magneto, it's just slower. But again, at the time, the storage was just great. In fact, I have a lot of experience with these. When I was an intern, I spent many, many hours copying files on and off of these disks.
That's a laser
so
disc.
it's not the first time that I've held one. They went through all the trouble of coming up with this magneto. So, at this point, it works just like a CD.
All right,
Now we want
don't have to worry about that mess.
Element for polarization is it'll rotate. The polarization direction will turn a little bit, and more and more and more and more, and it basically turns as it goes through the medium, and of course when it comes out, it's now rotated. So it's really the simplest kind of device you can imagine for rotating linear light. So it went in vertical and it comes out at some angle. So the angle you get, so if it came in like this and it exited like that, the angle is beta. If we call the angle beta, then we would say that beta is rho times d. So d is just going to be this distance, the thickness of the material.
What happened to v?
Something like that. And then rho is called the specific rotation.
These dudes like to write
And
on
it's in
chalkboards.
a unit of just degrees, usually per millimeter. So if you want to know how much you're going to rotate light, you just look up its specific rotation, you figure out how thick of a piece of material you need, and that's how much rotation you get. Now you could say, we have already rotated light with a wave plate. Remember, a half wave plate can be used to rotate light. But physically, they're very different. So the physical phenomena they use is different, but also the way you use them is different. This one rotates light by a set amount based on its width and its optical activity, and in its specific rotation, and that's really all it can do. A wave plate, it rotates light sort of by twice the angle, a half wave plate by twice the angle at which you have it relative to the linear. Cosine, sine, cosine, sine.
Is when an object, in today's case, a glass rod, when it's in a magnetic field, affects the polarization. So we have our vertical polarized light going in, the analyzer polar right over here in a screen where we can see what's going on. Here's a solenoid, which we'll use to create a magnetic field. Tucked inside the solenoid is a glass rod. I've got another one pulled out here so you can see what it looks like. It's just literally just a transparent rod inside a holder, so it fits inside the solenoid. So that's already tucked inside the solenoid. First, I'm going to cross the polarizers, so we're extinct. The beam is blocked. All right. Then I'm going to insert the rod, the Faraday rod, in here, so I can see light going through it. All right. And you can see very faintly the spot has come back just a little bit, indicating the rod itself, even without the magnetic field, is slightly birefringent because I can't actually zero out that little bit of light there. No matter how crossed I get the polarizers, even when they're 100% crossed, a tiny bit of light leaks by. So the rod, the glass rod itself, is probably very slightly birefringent. But that's independent of the effect we're looking at. We want to know what happens now when I apply the magnetic field. So over here, there's a power supply, and basically I'm just going to turn it on, and we can see we're now running about 3.1 amperes through the coil. So there's a magnetic field in there. You can see our spot has got a little bit brighter now, and I can try zeroing it out again. And I find I have to move just a little bit. The rotation is very tiny. All right, so when I find the minimum now, I find I've rotated it about 2 degrees counterclockwise. 2 degrees counterclockwise. Now I'm going to turn the magnetic field off and re-zero. There, all right, and then I'm going to reverse the magnetic field just by reversing the leads on the power supply over here and turn it back on again. 3.1 amperes. The beam is now a little brighter, and now I see I have to rotate.
That's killing electricity.
About 2 degrees clockwise now. So the direction of rotation has changed when I reverse the magnetic field for the solenoid. And this is what we call the DC Faraday effect, because we're applying a constant magnetic field, and so you just get a rotation proportional to the size of the B field. Using this setup, though, it's really difficult to measure how big that is, because at the maximum output of our power supply, we just get a barely detectable rotation.
What about an AC field?
But its polarization is unchanged. When light travels through a vacuum, even a big magnetic field doesn't affect its path. But when light travels through water or many other transparent media, the presence of a strong magnetic field along its direction of travel can rotate its polarization. This Faraday effect was first noticed by Michael Faraday as he searched for connections between electromagnetism and light. Remarkably, his discovery came long before James Maxwell's understanding of that connection. So now we'll explain the apparatus. So here we're using a green laser because it's easy to see and it's also easy to manipulate. So in front of the green laser we have a linear polarizer.
This
In
is
front of
in
that,
addition
we have
to what I was
two
studying.
coils that are acting as one long
I wanted to
solenoid,
study that
which is going to provide the magnetic field when we put a current through the
convex
coils.
mirror,
And
whatever
that
the
is
heck it
submerged
was,
in
thing.
water. And then in front of that we have another linear polarizer.
I'm wondering about combining
As
the
you
two
can see, when we
things
place
into
this
one
linear polarizer in
unit.
front of the laser beam, these two polarizers are oriented in a way such that they'll block out all of the laser beam when you place it in the direction, in the way of the beam. And now we will demonstrate the effect that the magnetic field produced by the coil has when we put a current through the wires. Now we turn the current on. Observe that the laser beam is now visible on the screen, and now we turn the current off. With the magnet on, the beam can again be zeroed by rotating the second polarizer 2 degrees. Reversing the polarity of the current reverses the sign of the rotation. When the beam passes through air, which is above the water level, turning on the magnet has no effect. Thank you for watching, and I hope you'll learn more about this effect in your physics class.
I actually like that first experiment better. Okay, now we're going to get back to this, and before I do, I want to grab me a little snack. And we'll just play some music here. And I'll be back momentarily. I forgot what the heck the name of it. Yeah, this is the device right here. The Fabry Perot interferometer. We're going to build this, and I want to see if I can mechanically improve the strength of the beam, the test beam, coming back. And I gotta redo my little setup over here because I'm going to move my test setup to a different area so I can get the camera connected to the computer and get more technical with this stuff. But I will be back momentarily because I'm going to get me a little snack. I gotta have a snack attack. testing. I'm getting excited. Getting excited like a magnetic field. And I just happen to have bought some veggie oil. Not for my interferometer. Take me down to the van by the river. Take me down tonight. Take me down to the van by the river, and everything gonna be alright. Oh, if you only knew. I'm working on cleaning my lenses. I'm looking at right now. I'm just turning my lenses over so they can dry. And I've got about 2 or 3 convex lenses, which is my only hope, Obi-Wan Kenobi, for my Faraday Perot interferometer, which is going to be added to my system of the main barometer. You know it, I know it, everybody know it. I'm out of ice cream. Ice cream for ice cream in the morning. Ice cream for ice cream at night. When ice cream for ice cream every day. Know everything gonna be alright, yo. I like this guy. I listened to him about this video, and it seemed like he was like really explaining what he was doing like really well in one of his videos. I don't know which one it was. Bet you get the idea. Jack, what if I could use that aloe? What would happen with aloe if I put aloe in there? Because that's like, that has a reflective medium. That's like an oil. And it's a lot more viscous. So what happens is the light slows down, and you look at it. Well, I guess he looked at it down the tube or something. I don't know what he did. I didn't know if you could look at it transversely and see a change, and then redirect that information back through the beam splitter. I don't know. Let's go ahead and turn this music off and listen to this video here.
Demonstrating how to set up and align a Fabry Pro interferometer. For our Fabry Pro, we're using custom-made mirrors that consist of a 1/2 inch round of fused silica, with one side with a radius of curvature of 75 millimeters, and the opposite side is flat. On the curved side, it has a reflective coating with a reflectivity of around 98 to 99% between the wavelength range of 820 nanometers to 960 nanometers. And the back side is coated with an anti-reflective coating within the same range. We've mounted our mirrors on standard mirror mounts. In one mirror, we'll mount directly to the optical table, and the second mirror will mount to a stage that has a piezoelectric actuator in it, such that we can scan the length of the cavity and create a scanning Fabry Pro interferometer. Now, for demonstration purposes, we're using open Fabry Pro cavity. An open cavity is susceptible to many different types of instabilities, such as air currents or thermal instabilities, but for demonstration purposes, it's satisfactory. Now, to guide the beam into the cavity, we'll be using 2 steering mirrors. And for mode matching, while there's several different techniques for mode matching, we'll be using a technique that utilizes a single lens. In this technique, we have our source that comes from an optical fiber, and we position our lens such that it focuses to the correct size that the cavity supports, and then we can set the length, the path length, such that the focus is at the center of the Fabry Pro cavity, and to finally adjust, we can use a stage. Now, we have a few other tools that we'll be utilizing. We'll be utilizing a camera to view the spatial modes, along with a monitor. Obviously a function generator to divot the length, and then to view the transmission of the modes, we'll be using a photodiode along with an oscilloscope. Now the first thing we have to do is go over some mathematical estimates to direct our setup. Constructing a Fabry Pro interferometer, there's several different parameters one can choose based on the desired outcome and needs of the interferometer. In our case, we already chose our mirrors, so what we have left to choose is the length of the interferometer, or the separation between the 2 mirrors. Now, we desire a free spectral range, or the separation in transmission peaks in frequency, of around 4 gigahertz. We can use this to find the length of the interferometer by setting it equal to an approximate formula for the free spectral range, which is just the speed of light divided by 2 times the length. And this gives us a length around 3.75 centimeters. Now, for our reflectivity and our free spectral range, this gives us a resolving power of 25 megahertz. The second thing we need to calculate is the beam waste of the Gaussian beam that our interferometer supports. Now, in our case, we can neglect the thickness of mirrors and use this formula that we obtain from laser beams and resonators. And this takes in a radius of curvature of 75 millimeters, a length of 3.75 centimeters, and a wavelength of 920 nanometers. And this gives us a beam waste, or W naught, of 100 microns. Now, the third thing we need to calculate is the separation between the lens and the fiber, and the lens and the center of the interferometer. Now, in our case, we can use the lens maker's formula, where S1 is the separation between the lens and the fiber, and S2 is the separation between the lens and the center of the Fabry Pro interferometer. Now, to get Y1, we can use the mode field diameter of the fiber, which in our case is a Thorlabs SM800 5.6 125, which gives a mode field diameter of 5.6 microns, and just divide that by 2 to get Y1. Y2 is our calculated beam waste, which is about 100 microns. And then to get F, our focal point, we can use our part number for the collimator that we're using that has a lens in it, which is the Thorlabs CFC8XB, which has a lens in it of a 7.5 millimeter focal length. Alright, now we can solve for S1, which is approximately 7.7 millimeters, and now S2, which is approximately 275.4 millimeters. Alright, now we can construct an interferometer. Alright, now we're ready to set up our system. It's always good practice to make sure your optical elements are around the same height. That'll make it a little easier to align the vertical angles. So the first step I have to do is I have to set up the Fabry Pro, right? So we have one mirror already secured to a stage that has a piezoelectric actuator in it. So we just have to secure the second mirror. Now, from our calculations, we want the second mirror approximately 3.75 centimeters from the first mirror. So I can just use a ruler to measure that. And
alright, before he goes any further, I gotta look something up here. Damn it. moving? It's moving. What the fuck? Can I use that to control the position of the mirrors? Secrets to precise movement.
That's because it uses an precision. I saw these actuators in a random post somewhere, and naturally I wondered how they work and how they are made. Long story short,
here we are at Xerion headquarters to uncover the secrets of precise movement. This video is not sponsored by them, so I can say whatever I want.
There is a fundamental problem when you try to move very precisely, and that is speed. Let's say we want to automate a microscope to accept a whole tray of medical biopsy samples.
Oh dear. Oh dear. We got a problem here. What did I do with my, I gotta find my candy bar, because I want to have a conniption if I don't have it. Piezoelectric actuator, baby. Take me down to the river. Move that mirror today. I need to move my mirrors in terms of like frickin' nanometers, you know? I have to have extremely sensitive adjustments for my mirrors. And I spent like, God, I probably spent $10 or $20 on screws, on 440 screws or whatever the heck it is, to do these adjustments and trying to do it mechanically. And now all of a sudden I'm discovering I can do it electrically. I could take all them screws back. I could get $40 back. Hi, I don't need all this hardware. I'm doing something else.
To see if there is any cancerous cells. We want the microscope to take a bunch of pictures, and a doctor or an AI then chooses some parts to take some more pictures from at a much higher magnification. So we need to move between samples that might be 100 millimeters apart, but we also need to do high magnification scanning, for which we might want a precision of about 100 nanometers, 1 million times smaller.
Nice.
Let's see what happens if we use the same mechanism that's in this micrometer. A screw. A beautiful piece of precision machining that has a thread pitch of 0.5 millimeter per rotation, about the same distance as the lines on a fingerprint. And one rotation is divided into 500 parts for the use of a vernier scale. By looking how these lines line up, you can see exactly how far I am between these two lines. In this case, 6/10. Anyway, 500 subdivision of 0.5 millimeter means that you can move this micrometer with a resolution of a 1,000th of a millimeter, or 1 micron. Sadly, this is still 1,000 times larger than a nanometer, and you can see already that even if you motorize this, it's painfully slow already. If we want a precision of 100 nanometers, for example, it would move at this speed. Imagine that, trying to move between samples. That's simply a huge waste of time. One of my favorite ways to actually get down to the nanometer range is through a flexure mechanism. If I push this down, these arms are pulled out a tiny little bit, and they in turn pull down the top an absolutely minuscule amount. This is great, and this type of mechanism can reach into the single-digit nanometer precision, but besides the fact that this can't move very far at all, it also has the speed problem. In fact, wedges, gears, screws, these flexure kind of mechanism, in fact, all mechanisms that are connected to an electromotor of some sort all have the same problem. They can only scale down movement together with the speed. So if you care about the relation between precision and speed, you need to look into a different type of motor and not into a different type of mechanism. a human hand can do about 1,000 to 10,000 of its smallest increments per second. I can keep my hand still with about a precision of 1 millimeter, and I can move my hand at a few meters per second, right? Stepper motors, servos, and other coil-based motors can do 10,000 to maybe 100,000 of the smallest steps per second, if you try really hard. But this actuator has a score of 5 million. That's because it uses an ultrasonic piezoelectric motor. Some crystals generate a voltage if you squeeze them. This is how these clicky lighters work. I can recommend Steve Mould's video about this if you want to know how the piezoelectric effect works on a molecular level. This effect is even how your phone is able to filter a useful signal from the electromagnetic noise all around it, if you remember my video about that. But importantly, this piezoelectric effect works in reverse too. If you put a voltage across these crystals, they expand or contract ever so slightly. And yes, PZT, the most commonly used crystal for this, is dark grey and not translucent. PZT expands or contracts basically linear with the applied voltage to a maximum of 0.2%, after which it breaks. You can get really precise with it, but with a crystal that's 1 centimeter large, the maximum range is just 0.02 millimeters or 20 micron. So, just like the flexion mechanism, it's extremely limited in its range, and on top of that, these crystals return to their original position as soon as you stop powering them. So, at first glance, this effect doesn't seem very useful at all. However, the movement is very fast. The piezoelectric movement through a crystal moves at the speed of sound, and in PZT, the speed of sound is more than 4 kilometers per second. So here we have something that can move very precisely and extremely fast. The only real limitation is the range, and that's where the motor part of this comes in. The simplest piezo motors are just one of these crystals with a piece of ceramic on the end that touches a ceramic bar. It moves out slowly, pushing away the bar, and then it pulls back very fast, making the contact point slip. And it does this over and over again, a few thousand times per second. It might be that the camera lens in your phone uses this type of motor for its autofocus. These inertia piezo motors are quite precise, in the low double-digit nanometers I believe, with speeds up to about 20 millimeters per second. So not a bad score at all, but that's quite slow compared to the other type of piezo motor we'll be looking at, because the high-speed movement is needed for slipping back and can't be used for moving forward. And another downside of inertia motors is that they wear out relatively quickly because they have a sliding surface. So they are generally not that great for industrial users that need to operate all day, every day. Xerion uses ultrasonic piezo motors. This type of motor also has a ceramic contact point, but the crystal is brought into resonance in such a way that the ball makes an ellipse and walks across the surface. This motor, the big one, can reach speeds up to 1 meter per second, 1,000 millimeters. It's so fast because it only contacts the surface when it's going in the right direction. So, in contrast to a stepper motor, these ultrasonic piezo motors actually take steps. I'll explain how this elliptical path is created in a minute, but let's see how they are made first. It's actually a very short process. They get small squares of the PZT crystal with a thin layer of silver on each side that will later become the electrodes that supply the voltage to the crystal. They cut these blanks into the exact right dimensions, and then they ablate some lines off with a laser to create the separate electrodes, 4 on each side. After that, they mill a hole in the center. Then they just need to solder the leads to it, glue a ceramic bowl to the tip, and fasten the mounting structure. And that's it. So how does it work exactly? Each electrode is paired up with the electrode on the opposite side, and both these groups are fed a sine wave. If the waves are in phase, you excite all 4 electrodes at the same time, which will make the crystal shrink and grow everywhere at the same time. In this case, the ceramic bowl on the end just moves in and out. If you have 2 sine waves that are completely out of sync, the crystal will shrink on one side of the ball and expand on the other side of the ball, making it move side to side. Now, by changing the phase of these 2 sine waves, you can make the ball follow an elliptical path, or a circle if you so wish. But remember, this is the resonance of the crystal, the same way a tuning fork might vibrate. It only works at one specific frequency that you actually have to find for every individual motor because they differ ever so slightly from each other. So you'd be forgiven to think this motor can only have one speed. But here comes the smart part. By changing the shape and to a certain extent the size of the ellipse, you can determine if the motor takes big or small steps, and you can change this on the fly to accelerate or decelerate. Before we get into all the other problems of small movement, let's go on a little bit of a tangent. I wanted to take high-speed footage of these two motors that I got to take home. But the slowest motor with the biggest movement makes an ellipse about 85,000 times per second. So I'd need at least 1,000,000 frames per second to film that properly. But then again, the ellipse is only a few microns wide, so I'd also need a pretty strong microscope. And that's not even taken into account whether or not the footage would be any good, because we'd need to zoom in so far that you could only see a line bobbing up and down. That's why I'm showing you animation instead, which brings me to the sponsor of this video, Skillshare. I wanted to make it look like these images came from an electron microgramming, product design, or using Skillshare for sponsoring this video, or that you need small movement. And, well, that all depends on how you put it down and how hard you squish it. For the increments, right, for the relative movement of measurement motors, and with the movement itself. Count and contract with them are exactly how good ultrasonic stepper motors. The last interesting difference I will note between piezo motors and geared down electromotors is backlash. Backlash does not exist for piezo motors because they're just straight in contact with their ceramic beam. But if you're working with gears and screws and whatnot, backlash can be a big deal. For gears to mesh together, they need a little bit of room. So when the gears switch direction, there's a little bit of rotation of the first gear before the second gear starts to move. When you have multiple gears in a row, the backlash can add up quickly, as you can see in this dial indicator. Terrible! And this is a measuring device, which of course is why it has a trick up its sleeve. It always loads the gears from the same side. The problem doesn't exist if you just don't switch side with gears. It does this with what's called preload. Look, it has a big spring to resist the movement and always push into the workpiece with the same pressure. But here in the back is a small spring that keeps tension on the system in the other direction from the last gear. So whether the dial is moving left or right, the gear touch on the same side, because the small spring keeps some tension in one direction. And a similar thing can be done for screws. Preload is not always a viable solution. It doesn't work if you need a lot of power, for example, and a lot of rotations can be a challenge. But for light and precise tasks like this, it works like a charm. Thanks to Xerion for showing me around and
So we're talking about piezo electric precise movement. The strangest motors you've never heard of. Ultrasonic motor, piezoelectric motor, 10 years ago. What's this one here? So I'm thinking in terms of moving those mirrors using, because once, so that means continually powering the unit. I'll be right back. So once you turn it off, then the mirror would go back to its default position, and I would have electricity running inside of that enclosure all the time. So in my particular system, that's going to be a problem. I can't have that ultrasonic deal is. We're sort of down in the middle of the rabbit hole. We're going to be coming back up shortly. I won't be here. I'm going to live a life of danger. I'm going to get some. You want to get some? Come on, boy. Come on, boy. Let's get some. Yeah, you know it. Uh-oh. Uh-oh. Yep. I played so many freaking video games for the last freaking 5 or 10 some odd years, you know? Now I'm getting to this way over my head. Well, it's not really way over my head, really. It's at my level of consciousness. Let's see what the hell we got here. Linear, small, precise, and fast. That's probably an advertisement. What's this one? Keymet. Piezo electric nanomotion system in the semiconductor field applications. Yada yada. Yada yada. Piezo ribbon sensor. That guy looks weird. Let's have a laugh and watch his video. Huh? The most accurate motor in the world. Wait, are we looking at videos? What are we looking at here? I don't want to look at garbage. Pizza motors. Piezoelectricity, piezoelectric effect, ultrasonic pizza motor, pizza, ultrasonic pizza motor. Yeah, boy. Piezoelectric fan. No moving parts. What's this? The Action Lab. This dude's around a lot. A high-speed linear action actuator. Wait. Piezoelectric, this is where we were, but piezoelectric actuator test. Flexible piezoelectric actuator. Holy shit, did you see that? Yeah, but then if you... Piezoelectric actuator and sensor. Piezoelectric actuator. Yeah, limitations of piezo and digital microscopy. Alright, let's watch this here. Yeah, real cute.
The ultrasonic motor is probably one of the more stranger designs out there. And instead of magnets or coils, it actually utilizes piezoelectric materials. The stator is made out of a piezoelectric material that generates vibrations when a voltage is applied. So this material undergoes a change in shape, or deforms, when subjected to an electric field, and it's able to return back to its original state in many cycles per second. There are many different types of piezoelectric materials, including natural quartz. This is probably one of the most widely used piezoelectrics, and in fact you are probably utilizing quartz in some sort of device today. It's very instrumental in timekeeping devices, including clock radios, cell phones, and even watches. when a current is applied to a quartz crystal, it vibrates at roughly 32,000 times per second. In this setup, it's pretty much a tuning fork with electrodes plated on the quartz, and the two tips will vibrate with a certain frequency. A microchip detects the crystal vibrations and then transforms them into electrical pulses. These pulses drive a small motor which converts the electrical energy into mechanical energy. As a side note, you can actually go further than this and utilize atomic oscillations which go up to millions of times per second. And with the right circuit, you can have one of the most accurate timekeeping devices in the world. But when it comes to motors, we want to keep the accuracy of a piezoelectric oscillation. The material still vibrates, and it typically creates a traveling wave within an ultrasonic motor. You can kind of think of it as a wave propelling a surfer. It's able to utilize this wave and move to a different position, and that's essentially what the rotor is doing without all the fun. So this deformation is essentially what is driving the motor. And it is true that we can take a material like quartz and utilize it in the stator. But unfortunately, quartz has limitations when it comes to manufacturing tolerances and geometries. So we have to actually fabricate something which can perform better in the motor. Today there are many different types of ceramics which contain inorganic materials like oxides and carbides. They can offer greater deformations, more complex geometries, so there are more options on the table when selecting materials for a piezoelectric motor. One of the front-leading materials right now is lead zirconate titanium. It has relatively good stability under stress with low dielectric loss, so it can operate continuously with minimal heating. Unlike quartz, it can be optimized to oscillate at a certain frequency, up to over 100,000 Hertz. So what kind of motor can you really design with a piezoelectric PZT material? Well, the truth is that there are many different variations out there, and the ultrasonic motor is just one of them. Now, these types of motors oscillate at frequencies above 20,000 Hertz, which is the ultrasonic range. And they can be very accurate up to the nanometer level with no backlash and a high holding force. They're lightweight and small, and can be used in anything from medical imaging to semiconductor manufacturing. But one of the most infamous applications is probably autofocus systems in cameras. In the 1990s, advancements in manufacturing lowered down motor production costs, and big players like Canon introduced ring-type ultrasonic motors into their autofocus lenses. This type of motor is powerful enough to drive the focusing lens group, so the rotor is not going to shift and the focus is going to remain stable. It was found very quickly that this motor was an excellent candidate for controlling direction, speed, and degree of focus adjustment. And even today, modern video cameras utilize multiple USMs. So have we finally reached the peak of piezoelectrics, and can it be advanced even further? Well, recently it has been discovered that these types of PZT materials can be actually used as actuators in flapping wing microaerial vehicles. There are no gears or reduction drives, motors, or even large propellers. And just like the ultrasonic motor, these piezoelectrics can create oscillating motion. One of the most infamous robotic insects is the RoboBee from Harvard University, and it utilizes strips of ceramic that expand and contract when an electric field is applied. A balance control system commands the rotational motions in the flapping robot, and each wing can be controlled independently. However, there are still problems associated with these types of insect drones because they need a self-sustainable power source, and they're not quite fully autonomous just yet. But it does show us that these types of materials can lead to very small microscopic drones. So when we look at the ultrasonic motor, it's definitely something that is not scalable into larger sizes. And that's simply because of how it's made. It's basically a material that oscillates with an input voltage. And when we get into these larger sizes, it starts...
I thought I'd make a quick video about something interesting I just came across. This will be a freebie video for my Patreon subscribers. And this is a piezoelectric motor. So let me show you how it works. This is just a plain piece of small glassware, and I'm going to put it on top of the motor and press the button. You can see it spins around. If I take the glassware away and press the button, nothing happens. So it's not like this is spinning, at least not macroscopically. But if you put a hard object, especially like glass on here, it spins it around, no problem. Pretty cool piece of tech. And so as you can see, this is PCBmotor.com. And what's happening here is each one of the little elements in this ring is a piezoelectric surface mount component. And if you create a wave that travels around this ring of components. As the wave travels around, the components contract and expand, and it creates like little
Pretty slick, huh? Yeah, that's what I need right there. I need that shit for my motor system, my mirror system. Yeah. 48 volts.
Multi-layer piezoelectric actuator. This provides piezoelectric actuators finally firing and baking the actuator. Of metal sealed type actuators for use in high reliability applications consist of the ASB. As the amount of data communicated.
Okay, well, I don't care about that one either.
Piezoelectric actuators use special materials that deform when voltage is applied, enabling incredible precision moments. They are widely used in medical devices, micropumps, and camera autofocus systems. The major advantage.
One of the most accurate motors in the world is based on the piezoelectric effect. Certain materials like ceramics can change shape when an external voltage
That's crazy, huh? Creating haptic feedback with piezo. What's this one here?
Hi guys, welcome back. In this week's video we're going to talk about piezos. I don't think I have ever mentioned these devices before on my channel, but there was a time where I was really into them. If you don't know what's a piezo material, it's basically a magic ceramic that generates an electric charge when mechanically deformed. So in simple terms, it's a force sensor. But what I find interesting about these materials is their converse effect, which allows them to create a mechanical strain when a voltage potential is applied. This means that they can also be used as buzzers or actuators. Now these piezos are usually designed to be used for specific applications. To give you an example, these are all the piezos I have here in my lab. These super thin ones are meant to be used as buzzers, which I'm pretty sure a lot of you have used. But there are also a lot of makers who use them as force detectors. Then here I have this piezo, which is intended to be used for energy harvesting, but back in the day I have also used this as a haptic actuator. This guy is now obsolete because I have ordered this in 2013 back when I was a student. I remember spending all my monthly income on two of these just to break one in like 5 minutes because they are super brittle. The last piezo I have here is a little bit more affordable and is specifically designed to be used for haptic feedback. It is priced at around 25 euros and from a 9x9mm footprint it can create up to 2.5 newtons. In the last few months I have done some experiments with this device to get more familiar with haptic feedback. The first thing that I did was get a special driver because to make a piezo vibrate it has to be powered with high voltage. And this evaluation board has a DRV8662 chip which contains an integrated 5 volts to 105 volts boost converter. This is powered by haptic feedback. I tried connecting one to the DRV8662 module and it actually worked and started vibrating around. Project happened, I needed to brush up on some analog electronics theory, so I decided to take this class by Leon Patron. Now let's continue our piezo testing. To try and get the best results, I'm going to compress the piezo inside the housing like this one. So since the power hub has wires, it's going to be housed in a 3D printed mouse, not touching the disc. In levels, the output stayed within 50 volts peak to peak. So the module is like a real click. To use the piezo as a buzzer, I just drove the same sine wave at higher.
Hey everyone, today I'm going to be showing you how a solid state fan works. It's going to wear out and break. And also because it's compression. So if you layered the piezoelectric so that the bottom was getting compressed and the top was getting pulled on, then that means just by applying a voltage, you can make something bend. And that's exactly what I have here. So this piece is a piezoelectric so that when I apply a voltage, it's going to bend one way. But then if I reverse the polarity, it's going to bend the other way. And on the end here, I just have some plastic attached to it. So that means if we apply an alternating current back and forth here, it should be able to bend this back and forth really fast and flap that plastic. I have these two wires here connected to the regular outlet in my house, so it's alternating current 120 volts at 60 hertz. In order to get this vibrating at the maximum amplitude, that means I have to match the resonant frequency of this vibrating plastic to 60 hertz. So what I've done here is just added tape to it until I got the maximum amplitude of the vibration. Now let's turn on our piezoelectric fan and see how much air movement we get. All right, let's go ahead and turn this on. 3, 2, 1. There we go.
Oh my God.
So we get a really large vibration out of this. So let's see if it's actually blowing air now. It easily blows out this lighter here. Because there's no wearing surfaces, piezoelectric fans like this can last for billions and billions of cycles. In fact, I just saw a video where a guy's been running his piezoelectric fan for over 6 years straight and it hasn't broken down yet. That's because everything that's moving is well under the elastic limit and there's no friction parts, and so there's nothing really to wear out. Now you can see that we can get some really good airflow going here, but it's not quite the airflow that you get with a high-powered fan. But in applications where you don't need a ton of airflow, but you just need a little bit more than natural convection, these piezoelectric fans work really well. For example, in space modules where you have people living, any electrical components heat up really easily in there because normally hot air just rises and gets out of the way, so you have natural convection. But if you're in space, there's no buoyancy, and so that hot air just stays in place. So you need some extra forced convection to get it out of the way. Another application of these piezoelectric fans that's really neat is with a regular fan, you have turn on the power and it has to spin up to speed before you get a specific output out of it. But for this device, the power up is instantaneous, so it starts vibrating back and forth at exactly the time that you apply the voltage. So that means you can get really precise temperature control with a piezoelectric fan where you need to turn it off and on and turn it off and on really fast and not wait for some rotor to speed up. So what's your opinion? Would you put a piezoelectric fan in your computer to cool off the components? Now before we end, I'd like to thank Squarespace for sponsoring this video. Squarespace Extensions. This Action Lab to save 10% off.
Okay. Now look at this video here. Well, that was short-lived. Okay, getting back to what we were doing.
Miday's range of quick packs can serve as piezoelectric actuators and sensors. Seen here as an actuator operating a flow control valve, Miday's quick packs offer precise variable frequency and amplitude actuation, which means an operator can control how fast, slow, high, or low the piezo actuator is driven. The piezo itself is protected using Miday's Piezo Protection Advantage to hermetically seal and protect it from harsh environments, whilst also providing electrical insulation around the piezo.
But the datasheet doesn't directly state this, although it does imply they contain lead by warning that they shouldn't be disposed of in a landfill. When a positive voltage is applied to the terminals, the length of the device increases by a small amount. For this device, the behavior is roughly linear, and a maximum displacement of 25 micrometers can be expected at 75 volts. The spec sheet provides a tolerance of plus or minus 15% on the displacement per volt, so my goal is to measure this and ensure it is within spec. For my application, the force generated by the transducer is somewhat more important to provide a stable platform. Powering the actuator is a linear DC power supply capable of outputting up to 120 volts and 1 amp. Although for this setup there will be negligible current and the voltage only needs to go up to about 80 volts. Here's a plot provided by the datasheet showing the expected behavior of the device versus voltage. Two curves are block was a lucky find in my garage. It has just the right dimensions to hold the actuator and allow the probe tip to fit inside. It ensures that the actuator stays perfectly perpendicular to the granite surface, and it makes it easy to slide the actuator around until the probe is perfectly centered such that its force is directed down through the piezo stack without imparting any off-axis loads. Stacked piezoelectric actuators are very strong under compression in their long axis, but they are very fragile to other forces or torques, so one must take great care to ensure that they only ever experience compressive forces and never any tension, torque, shearing, or emotional loads. After situating it in the 1, 2, 3 block, I then connect the power supply and finally the multimeter clips. Before beginning the test, I want to know what to expect, so I need to calculate the displacement per volt. I divide 25 micrometers by 75 joules per coulomb, also known as volts, giving a displacement slope of 0.333 micrometers per volt. I intend to gather 8 data points from 10 volts to 80 volts, so the expected displacements are about 3.33, 6.66, 9.99 micrometers, and so on, as you can see on the calculator display. I could have chosen to gather 10 data points, but 8 is a power of 2, and as an enthusiastic dabbler in the company...
I'm gonna buy it. Buy it now. Let's go to Amazon. Piezo. It's that linear one. Pizza buzzers. Oh, there's a whole crap load of pizza discs for $5. With that cute little function generator, 1 kHz to 150 kHz pulse width modulated motor speed regulation. Pretty sick, huh? Flexible polymer film sensor microforce pressure transducer for measurement. Ultrasonic vibration plate for home electronics assembly generator. Piezoelectric film, high sense pressure. We don't really need that. Electromagnet linear solenoid. See, this mirror, these mirrors are going to be mounted on springs. I'm dying here. We whip into the $30. Okay, where were we? Back here?
Since we're using curved mirrors, we can just visually align these since the alignment requirements are much
actually
less
using
stringent than flat mirrors.
Curved lenses.
So it's about 3.75. So I'm just going to attach this mirror.
Because I don't have curved mirrors.
Alright, so the mirror is pretty well attached. Now the second step is I'm going to have to adjust this this lens such that it focuses down to around 275 millimeters for our wavelength, which is around 920 nanometers. So I can view the beam on a card, a viewing card, since we can't see the near infrared with our eyes. And now that I know that it's starting out, in our case we're starting with a collimated beam, which means that essentially it's focusing to infinity, which means that the lens is approximately the focal distance from the source or the tip of the fiber. So that means it's around 7.5 millimeters from the fiber. So I just have to adjust it further away from the fiber to get to approximately 7.7 millimeters, which will focus down to 275 millimeters. Also, the red laser will directly pass through both mirrors because it's not reflective at that wavelength. So I'm just going to adjust this so it hits the first guiding mirror in the center, and then adjust it so it hits the second guiding mirror in the center. Alright, and adjust the second guiding mirror so it hits the first Fabry Perot mirror in the center. Alright, there we go. So now I'm going to do a rough walking the beam procedure where I adjust the first guiding mirror such that the beam is at the center of the first Fabry Perot mirror, and then the second guiding mirror such that the beam is at the center of the second guiding mirror, or second Fabry Perot mirror. There we go. There we go.
And we saw this done with the
Just make sure, come back a little bit. Alright, so this looks pretty good now. Now I can firmly attach all the optical elements.
He's just doing this by eye.
Alright, so lastly, while the red beam is still here, I'm going to introduce this viewing camera using the red beam. Positioning it so the red beam's at the center of it. Alright, now we're ready to reintroduce the 920 beam and finally align the Fabry Perot. So I reintroduced the 920 nanometer laser into the system, and we're currently viewing the transmission from the camera on this screen while simultaneously dithering the position of this mirror and hence dithering the length of the cavity. Now, as we can see on the screen, it's this weird oval shape in transmission. So what we need to do is we need to adjust both these two guiding mirrors such that this oval shape collapses down into a singularity or a dot.
That I wasn't even
Now,
planning on using
in order
in
to do
my
this, we're
setup.
going to use this procedure,
And
this
I
walking the beam
figured out
procedure
that
that
I
we've
needed
used
to
in
use
several
them,
other
but
videos,
not for this
where
purpose.
we move one mirror and then compensate for the other. And we do this both in the horizontal and the vertically separately. So how I'm going to start this is I'm going to adjust this closest mirror such that this thing kind of collapses in on itself a little bit and we start to see these fringes. Alright, so now I'm ready to start with this horizontal alignment. So first I'm going to move the closer mirror, and then I'm going to compensate with the other mirror and bring it, move it out and then bring it back.
He lines that up.
And I'm going to keep doing this wider, and the fringes will be less and less horizontal. So I'll go back to where I was. Alright, so now you can start. Alright, so if we take a look at the oscilloscope trace, you can see a couple things I'm displaying. One, the voltage from the photodiode, which is the transmission of the cavity. We can see that we have the fundamental mode, and then we have a couple of higher order modes. And then back again to the fundamental mode. And I'm also displaying the voltage sent to the piezo, which is scanning the cavity length over a range that includes two fundamental modes, which means I'm scanning over a range of approximately the wavelength divided by 2, or in our case 460 nanometers. Another thing I'd like to point out is this pattern, right? This pattern of the fundamental mode and then the higher order modes of the fundamental mode is periodic. So if I change the offset length of the cavity, I get back to the original pattern. To do this, we took an oscilloscope trace of the transmission through the Fabry Perot. This way we can solve for R, which gives us a reflectivity of 98%, which is within
So he was talking
an
about
actual instrument to be within the
the reflectivity of the mirrors and the Pro.
is also referred to as the external cavity. For this demonstration, we have mounted a laser diode and a commercial mount that is both temperature and current control. We have also adjusted the outgoing lens such that the outgoing beam is collimated. Secondly, we have mounted the diffraction grating on a commercial mount that is adjustable in the horizontal and vertical angles. We have modified the commercial mount by attaching a mirror that faces the diffraction grating and moves along with the angle of the diffraction grating. When working with an open beam, and especially when introducing a new optical element, it is a good safety precaution to use glasses, because you'll never be 100% sure how the optical element will interact with the beam for the first time. Prior to this demonstration, we have calculated the horizontal angle needed for the diffraction grating, based on the laser diode frequency and the groove spacing of the diffraction grating. We have oriented our diffraction grating such that the grooves run vertically. When a diffraction grating is introduced into an oncoming beam, two important things happen. First, the beam is reflected off the diffraction grating, and then, in our case, reflected off this mirror and sent out of the system. This beam is referred to as the zero-order maximum. Secondly, the diffraction grating produces two first-order diffracted maxima, one in the outgoing direction and one in the backwards direction towards the laser diode. For this demonstration, we'll be using one of two geometries available for an ECDL, the Lithrow geometry, the second being the Littmann-Metcalf geometry. In the Lithrow geometry, we directly send the first-order maxima back into the laser diode such that we can tune the lasing frequency by adjusting the horizontal angle of the diffraction grating. The mirror that we have mounted facing the diffraction grating compensates for small changes in the angle of the diffraction grating and keeps the outgoing beam in relatively the same position. This setup is typical of many commercial products or laboratory setups, except for two major differences for demonstration purposes. First, our external cavity is much larger than needed. And secondly, we have mounted it on an optical table out in the open, where a commercial product would be enclosed and stabilized. For this demonstration, I'll be showing you how it is easily located. Alright, so it looks pretty good when you touch this knob. Now I'm going to adjust the vertical angle such that the first order maxima is open to take advantage of a trick within the laser diode. It's beam from the laser diode, and we can no longer distinguish between the two. We can no longer visually align it. This means we have to take advantage of a trick within the laser diode. If we turn the laser diode's current just below the lasing threshold, when we introduce the extra light from the first order maxima back into the laser diode, this extra light will cause it to start lasing, and there will be a noticeable difference in intensity in the outgoing beam. So the first step is to lower the current of the laser diode just below the lasing threshold. The laser diode spec sheet should state the lasing threshold current, but we can also inspect the outgoing beam. So I'm going to lower the current now.
I got a couple of lasers
Lowering the current.
I have to
There we
wire
go.
up.
Now it's no longer lasing. Let me show you that
They
again.
were done by
Raise the current,
batteries and the switches
lasing.
broke, so now I can see
Now
a
lower
need
the
for
current.
decreasing
No
the
longer
intensity of the beam.
There we go. Now the current's set such that the laser diode is just below the lasing threshold. Now I can proceed to adjust the vertical angle. Since first order maxima is below the laser diode, I'm going to adjust the angle up. So I'm adjusting up. There we go. You see that? A slight increase in intensity. And I'm going to continue adjusting up. There we go. Now there's a dramatic increase in intensity. Now I'm going to continue adjusting up and misalign it. Alright, so now I'm going to adjust it back down and align it again. As you can see, it's no longer lasing. I'm starting to laze, and now it's reached a maximum intensity. Now the angle of our diffraction grating is set such that we're setting the first order maxima directly back into the laser diode. Now, if we adjust the horizontal angle, we can change the lasing frequency of the system. And now we'll analyze it with a spectrometer. Alright, we directed the outgoing beam into a spectrometer for analysis. Now, as you see, as I change the horizontal angle of the diffraction grating, it changes the lasing frequency of the system. When I reach the end of the range, it jumps back to the natural lasing frequency of the diode. The laser in free space into an optical fiber. This consists of 3 steps, going from coarse to fine. The first step is to align your optical elements with the table. The second step is to align the incoming beam and a back-propagating alignment beam at 2 locations. And the third step is to optimize the coupling using a technique called walking the beam. Now first off, I want to go over some of the equipment we're going to use for this procedure. These mirrors have fine adjustment knobs. The top knob adjusts the vertical angle, and the bottom knob adjusts the horizontal angle. These mirrors can be clamped down to the table in virtually any position using these clamps. Obviously, we're going to need a fiber to couple into, and we're going to need a back propagating laser that's already coupled into a fiber.
So the whole problem with my setup is going to be temperature and humidity control. It's going to be an enclosed environment, and I need to be I'm going to be changing the wavelengths of the frequency, and when the wavelengths of the frequency change going into the beam splitter, the adjustments of those primary mirrors with that light going through there is going to have to I have to recalibrate it at that new color. So that may or may not be a problem. But I got to have a way to adjust those mirrors outside of the enclosure.
Now, to make sure the height is approximately correct for all our optical elements, we can use a ruler such that the beam hits the center of the mirror as close as possible. Now it looks like this one has to come up a little bit. Now I can use the holes to place the fiber coupler. So this center is about this. You just follow it out and then turn the mirror. And so if both beams are aligned at 2 points, that means they're collinear. The way to do this is to adjust the mirror further away from the point you're working with. So in this case, I'm going to adjust this mirror. And this will move the infrared beam. So I'm going to move the infrared beam until it overlaps with the red beam.
So that was mentioned
now I need to go to the other point.
You adjust the one furthest away from whatever the hell it is.
And move the mirror further away. This will move the red beam. So I'm going to move the red beam to overlap with the infrared beam.
You adjust the one furthest away from
So I need to go back to this point because adjusting this mirror slightly changes it. So now I need to move the infrared beam back onto the red beam. And just keep iterating this process until you get them as close as possible.
Yes, sir. Will do. Roger and out. I gotta get out of here.
Alright, so that looks pretty good. So now what we can do is check the back end of the fiber and see if we've coupled any of the light into it. As we can see, there's just barely coupling in, so now we're ready for the next part. Now that we've just coupled into the fiber, I can take the back end of the fiber and place it on the holder. The first thing we need to do is figure out how much we can couple into this fiber. And to do that, we need to measure the power that's going into the lens. So it looks like we're about 8.8 milliwatts. A good rule of thumb is a minimum of 50% coupling. So that means we need to couple in at least 4.4 milliwatts. So I place the head of the power meter at the end of the fiber to measure how much is actually being coupled in. The first step is to optimize each mirror independently. So I'm going to start with this one's horizontal knob and turn it clockwise. Alright, so I'm lowering the power, so that means I'm going the wrong direction, so now I need to turn it counterclockwise. So it looks like our maximum is around 25 microwatts. Now I'll do the same with this one's vertical. So I'll turn it clockwise, which is raising the power, so I'm going the right direction. Alright, now I'm going back down, so I need to back up a little bit because I passed the optimal point. So about 30 microwatts. Now I can do this mirror horizontal.
So now he's doing
so I'm going down, so I need to turn it the opposite direction. I'm actually able to get back up to 120, so that means I started turning. So through doing this many times. First is
precision rotation mount, power sensor, and a power. If you have linearly polarized light that is parallel to your slow axis, then you'll get that same linearly polarized light through your wave plate. However, the wave will be delayed by a amount that's proportional to the refractive index parallel to the slow axis and the thickness of the wave plate. Now, the wave plate has what's called a retardance. And the retardance tells you how much more of an offset you have due to the slow axis compared to the fast axis. Your polarizer with respect to your table, but we're not overly worried about where the transmission axis is. So we're just going to put it down arbitrarily. What we'll set up but you really need to see what I'm doing. So right now we're just using a lens tube between my power sensor and my mount to block out as much of the ambient light as possible. So I begin by using the coarse adjustment to minimize the transmission. And when I'm close, I'll lock down the coarse adjustment and use the mic to find the minimum.
Okay, well, I don't know what he's doing. Anyhow, that's got to be the end of my stream. I'm wanting to put veggie oil in a glass tube inside of a electromagnet, use that enclosure, and put the convex lenses on either side of that system. But I wanted to have a slit in between, in the middle of the thing. I wanted to combine the Fabry Perot interferometer with the with that Faraday effect. You know, like I'm doing two things at once. Then I probably would have to have I would have to have a camera looking 90 degrees to that Faraday unit. The Faraday is to see the change in the light intensity with magnetism. Yeah, that's exactly what I need to do. So maybe I could just make a quick note of that on the next page, or I could just do it right here on the same page. So we could do, like, we get the convex lens. Okay. We've got polarizer, and we've got, so we got BS, and we've got polarizers. Here. Zero and 45 degrees. And beam splitters at the end of the, so then we've got a glass tube. With veggie oil. And then we've got, they used, I noticed the one that worked the best had the coil around the tube. Like this. So we've got a solenoid with 2,000 turns. We've got the veggie oil in the middle. We've got, I don't know how that's sort of like a, yeah, I've got some convex lenses, and I think they're fairly small. There's a solenoid out there in my truck. I may have a couple solenoids floating around. Maybe I can use two of them. And we may be able to drive this a voice driver amp into the solenoid for a transmitter. Holy shit. So that's interesting. And then we've got, yeah, that's real interesting. That's very interesting. This is a new addition to the system. So we've got the solenoid around the veggie oil, and then the light, the different values of light going through the veggie oil, and then outside of that Faraday unit, there could be test objects, or there could even be a test object inside of the glass. The test objects could be small and fit inside that glass. Then I've got the Schlesinger effect parabolic mirror in behind all of that. The actual, that mirror is actually convex anyway. We may be able to use that and add the slit at the same time. So we've got a Faraday Fabry and Schleiger, whatever the hell that's called, all in one unit. Sweet Jesus. And I'm done with the stream. That's a bunch of theory. We've gone into the tuning of the interferometer. We've gone into the camera. Now I'm going to go ahead and, I've got about a half an hour, so I'm going to go ahead and set this stuff up. And then later tonight, I will go ahead and see if we can work with it. I still have to build my FET amplifier setup. I got to do voltage. I got to do power supply voltage setups. Lots of stuff to do. Interesting. Yep, I'm done for today. Thank you. Have a nice one.